Hello and welcome to Sleepy Science. I'm so glad you found your way here. Tonight, we'll drift softly through a gallery of impossibilities that somehow make our universe work. Light that paints interference like a wave and then clicks like a particle. Objects that tunnel without crossing the gap. Emptiness that weighs and even pulls plates together. Stars that fall toward infinity and still bend time. And black holes that seem to erase information even as Hawking's quiet radiation whispers it back. We'll float past galaxies that recede faster than light without breaking any rule. Clocks that slow in gravity, twins who age apart, and choices that appear to rewrite the past. We'll rest inside fields that ripple reality, stop light and store it like memory, feel temperatures below absolute zero, glide on superfluids, and listen to time crystals that tick without using energy. We'll notice shadows that outrun light, warmth born from motion in the Unruh glow, forces from the vacuum, dark energy that pushes everything apart, matter with its missing twin, hidden dimensions, and equations that predict all this without ever using time. This journey is gentle and strange, like a dream that teaches as it calms. Before we begin, I'd love to hear from you in the comments. Tell me where you're listening from, or just say hello. And if these quiet explorations help you rest, a simple like helps other sleepy minds find their way here. Now take a slow breath, let your body sink into comfort, and together let's begin our unhurried descent into the shimmering edge of what we know. Light that behaves like waves until it becomes particles. You notice it first in the quiet. A beam of light looks so simple, like a ribbon drawn across the dark. And yet the moment you ask what it really is, the world answers with two voices at once. One that ripples like water, and one that clicks like rain on a tin roof. And your job is not to choose a favorite, but to understand how both can be true without lying. So start here, gently, with something you can picture. A pool you once skimmed a stone across, the ripples spreading, overlapping, making bright and dark rings where peaks met peaks and troughs met troughs, because that is what light does when you let it roam. It interferes with itself like a wave, painting stripes of brightness and darkness on a screen, even if you send it one tiny packet at a time. In the famous double-slit experiment, you aim light toward two thin openings, and far away, you don't get two neat bands like you would with pellets. You get a whole barcode of bright and dim lines, a signature of wave-like behavior that says, I didn't choose one path, I explored possibilities and added them together. And the part that bends your intuition is this. You can turn the light down so low that only a single photon travels through the apparatus at a time, and over minutes or hours, each photon still lands as a single sharp dot, a particle-like event. Yet the dots build up into the same wavy interference pattern, as if each photon somehow kept track of both slits. That is not a magic trick or a mind game. It's the ordinary language of the quantum world, spread out as a wave to travel, show up as a point when you are found. And physics has learned to live with this without pretending it's one or the other, because wave and particle are our old words for behaviors that light can display depending on how you ask the question. When you install a tiny detector at the slits to find out which hole a photon goes through, the striped pattern fades away and you get two simple lumps. The photon leaves a trail like a little bullet, the interference vanishes, and you feel tempted to say your act of watching forced light to become a particle. But it's not your eyes or your wishes that do the changing, it's the interaction. The detector has to touch the photon in some small way to learn its path. And that touch shakes the delicate phase relationships that made the stripes possible. A process called decoherence that scrambles the ripples so they can't add up into bright and dark bands anymore. Notice the important nuance. You can even hide the data or throw it away. And as long as the setup could, in principle, have revealed a path, the stripes are gone, which tells you that information and interference are two sides of one rule. Know the path. Lose the pattern. Keep the pattern. Forfeit the path. None of this means light is indecisive or mystical. It means the best model we have treats a photon as a quantum state that spreads like a wave to predict probabilities and then produces a single, localized outcome when it interacts strongly enough to leave a mark, like a pixel lighting up on a camera sensor or an electron popping loose from a metal plate in the photoelectric effect. Discrete, countable, unmistakably particle-like. Everyday technology has bet real money on this dual character. Your phone camera counts photons. Fiber optic. Cables rely on interference to keep signals clean. Lasers harness billions of photons marching in phase like a regimented wave, while the smallest detectors still register them one by one, click by click. If you want a feel for how the wave part behaves without a single equation, think of color as the tempo of the wave. Blue light with its tighter wiggles carries more energy per photon than red light with its looser ones, and think of bending light with a lens as changing the travel directions of many tiny ripples at once so they meet in focus. Think of a mirror not as a silver surface but as a disciplined team of electrons that jiggle in step with the light and send the wave back as if the surface were another pond, and the angle of reflection were just the geometry of ripples arriving and leaving. But then remember the particle voice too. When that wave meets a screen, it doesn't smear a little energy across many pixels. It chooses a single spot, and the probabilities that predict where it might appear are drawn from the very same wave that spread out earlier. This is not a contradiction, but a partnership. Propagation uses wave-like rules, detection produces particle-like events, and the experiment you build decides which features you invite to the stage. Ask light to interfere with itself, and it performs like a wave. Ask it to declare which path it took, and it answers like a particle. Ask both at once, and nature refuses. Not because it is stubborn, but because the conditions that create reliable path information are the same conditions that erase the phase harmony required for interference. It helps to set aside the idea that your consciousness is the magical switch. What matters is the physical interaction that can, even in principle, record a path. A scattered atom, a warm detector, a trace left in the environment. Once that entanglement happens, the delicate pattern-making ability is gone, not by superstition, but by the bookkeeping of information. If you keep the environment quiet and the detectors out of the way, you can watch the faint interference build, dot by dot, as if the photon tested all available routes and let the routes vote on where it should show up. While if you couple the photon to a path meter, you trade that collective vote for a single declared history. None of this lets you beat causality, send messages faster than light, or harvest free energy. The rules are strict even if the pictures are flexible, and the universe never pays out on loopholes that violate its accounting. What it does offer you, though, is a deeper sense of honesty. That our old categories, wave, particle, were never the things themselves, only the masks that certain experiments coax into view. Light is quantum, which means it behaves according to a mathematical object that evolves smoothly and then yields specific, countable outcomes when it interacts. And if that sounds abstract, look again at your daily life, where both faces show up without fanfare. A rainbow is a wave sorting itself by tempo in droplets. A solar panel is particles handing energy to electrons like coins. A hologram is interference frozen into geometry, and a dim starlight photon, traveling for ages across the dark, still arrives as a tiny, indivisible click in a telescope. A single vote cast by a wave that explored the cosmos. If you carry one lesson forward, let it be this. You don't have to choose what light really is to appreciate what it does. You only have to ask clear questions and notice how the answers depend on the way you ask. Because that's not a flaw in reality, but a feature of it. And once you accept that, the mystery softens, not by becoming smaller, but by becoming livable. So, you can stand in the gentle glow of evening, watch the color of the sky shift with the sun's angle, and feel a quiet gratitude that the same phenomenon can sing in two languages without ever telling a lie. Objects that move without moving. The tunneling mystery. You hear the story in old fairy tales first, the one where a door is locked, and yet the hero appears on the other side, and you assume it is a trick until physics tells you that the smallest pieces of nature quietly do this every day, not by breaking rules, but by following deeper ones. And that is the strange comfort of quantum tunneling, an effect that lets an object arrive beyond a barrier it does not have the energy to climb in. Any classical sense, as if a mist could pass through a mountain without drilling a hole. To picture it, imagine a smooth hill between you and a hidden valley. A marble rolled from your side will usually roll back because it lacks the push to crest the top. Yet in the quantum world, the marble is not just a point, it is also spread out like a calm, low tide of possibility that seeps a little way into the hill. And if the hill is thin enough, there is some chance for the spread to reappear on the far side, and then the marble is found there when you check, not because it cheated, but because the laws that govern its spread allow a sliver of its presence to leak through, a chance that falls off very fast as the hill gets thicker and higher, so fast that a hair more thickness can kill the effect, and a hair less can let it happen often enough to matter. This is not hand-waving, and it is not magic either. It is tested in laboratories, and it is wired into technology. You touch each day, for example, every time an electron leaves a sharp metal tip in a strong field inside a modern electron microscope. It leaves not by heating to a boil, but by tunneling out of the metal skin into the vacuum. And every time your camera or laptop writes to flash memory, thin insulating layers allow electrons to tunnel into or out of a tiny floating gate. So a 1 becomes a 0, or a 0 becomes a 1. The same effect lets the scanning tunneling microscope read the shape of a surface, one atom at a time, by hovering a needle above it and measuring a current that exists only because electrons tunnel across a gap thinner than a nanometer. This current drops dramatically as the gap widens, which is why the tool can feel the bumps of single atoms, and it was with such a tool that researchers once spelled 3 letters on a metal surface using xenon atoms, a stunt that was also a quiet proof that tunneling is real and controllable. Nature uses it in grander places too. Inside the heart of stars, the temperatures are fierce, but not fierce enough for simple head-on collisions to always push protons over the electrical repulsion that keeps them apart. Tunneling tips the balance. By giving those protons a chance to end up close enough for the strong force to grab them, without tunneling, the sun would need to be hotter and brighter to fuse as it does, which would have changed the story of our world. In a different corner of the nucleus, tunneling explains why heavy elements sometimes spit out a chunk made of 2 protons and 2 neutrons. That chunk would be trapped by the nuclear wall from a classical view, yet it shows up outside as alpha, decay with a lifetime that can be predicted by treating escape as tunneling through the nuclear barrier. Engineers weave tunneling into circuits in quieter ways as well. A tunnel diode conducts in a curious backward slope over a small range of voltage because tunneling offers a path that normal conduction does not. And in the realm of superconductors, thin barriers between 2 superconducting metals let paired electrons tunnel as a team with a rhythm that depends on the voltage across the barrier. The Josephson effect. This is the heartbeat of many quantum bits today, and the link that allows exquisitely sensitive magnetometers to hear fields that would otherwise be silent. Even in chemistry, a light particle such as a proton can sometimes tunnel between 2 sites in a molecule, rather than climb the energy hill in the usual way. And there is growing evidence that enzymes can take advantage of this in a few reactions, by shaping the landscape so the thin place in the barrier aligns with the path that matters, though the effect is subtle and not a magic wand. And in biology, there are careful studies that suggest rare quantum jumps of hydrogen atoms in DNA may underlie a small class of mutations, not because the universe wants drama, but because the laws it follows make the rare possible. The part that often invites arguments is time. People ask how long tunneling takes and whether something travels faster than light inside the barrier. The honest answer is that the question is tricky because the word travel assumes a path like a tiny ball rolling through a pipe, while tunneling is the reappearance of a quantum object on the other side when the conditions allow it. Experiments that time the exit using ultra-fast pulses suggest that the delay is very small and does not allow signals to carry information faster than light. In other words, you cannot use tunneling to send a message that outruns causality, the Universe keeps its speed limit intact even when it allows this quiet shortcut. To keep your sense of reality steady, note what tunneling does not do. It does not create energy from nothing. An electron that tunnels out of a trapped region still carries the same energy it must carry to be consistent with conservation, and it does not give you a free pass through any wall you choose. If the barrier is thick enough or high enough, the chance becomes so tiny that the event will not happen within the age of the universe. This is why certain radioactive isotopes have half-lives that span billions of years while others decay in a flash. A minuscule change in barrier shape often spells the difference. There is a human lesson in the physics too, because tunneling is a precise example of how the world is not always limited by the local picture you carry in your head. A person standing before a wall thinks only in terms of push and climb. Yet, the deeper rules say that a tiny part of what something is does not live only in the spot where you would point a finger. A little of it lives inside the spaces around it, and that little is enough to leave an imprint on the other side. If the spacing is right, the effect teaches patience and scale and humility. It says that when we say impossible, we often mean that we have not looked closely at how thin the wall really is, and it reminds you that nature is not obliged to follow the stories our ancestors invented, when all they had were stones and hills and keys that turned in locks. The practical takeaway is simple and concrete. Modern electronics would not be the same without tunneling. Starshine would not be the same without tunneling. The quiet tick of a superconducting circuit that forms the core of a quantum computer would not be the same without tunneling, and your own curiosity would be poorer without it. So the next time you press your fingertip to a window and feel the hard refusal of glass, try to remember that the refusal lives at your scale. At smaller scales, the universe is softer in certain, very precise ways, and in that softness lurks one of the most fruitful truths in science, that sometimes arrival does not require a path, only a possibility and the right distance for it to become real, energy that appears from nothing and then disappears again. You expect nothing to be empty, the way a quiet room is silent when the guests have gone home. Yet when physics turns out the lights and listens closely, it keeps hearing a faint rustle. In the dark, a kind of restless breathing that never fully stops. And that is the first unsettling truth in this story, that even in perfect darkness with all lamps off and all fires cooled as far as nature allows, there is still motion and still energy, and it is not a poetic metaphor. It is the baseline activity that quantum fields carry in their lowest possible state. The way the ocean still lifts and settles, even on a windless day, and the way a violin string that is not being played still has a tiniest tremble in its wood, since the laws that fix position and motion cannot settle to zero at the same time, without breaking the very rules that make them meaningful. So when we say energy appears from nothing and then disappears, again, we are describing this jitter of the ground itself, a dance that does not violate conservation because it is not money pulled from a wallet and spent. It is more like coins ringing inside a sealed jar that never opens. The total stays the same, yet inside the jar the coins keep clinking, and their tiny collisions leave marks that a careful ear can hear. You can find those marks in ordinary matter and in precise experiments, which is the most persuasive part of the tale. An atom that should happily hold an electron in a neat orbit, according to simple textbook rules, actually sits at slightly shifted energies because the restless field nudges that electron in subtle ways. This shift was first measured in hydrogen long before anyone had the full modern theory, and it was a shock. Then it became a pillar of the new view that empty space is not featureless, but has structure that can change what atoms do. The same restlessness helps explain why an excited atom gives off light on its own. Even when it is placed in darkness, there is nothing there to push it, and yet the atom decays the more. Accurate telling is that the atom is always coupled to the underlying field that already contains a whole zoo of potential vibrations, and those vibrations offer a path for the atom to let go of its energy. The vacuum is not a mute stage. It is a partner with just enough whisper for the atom to hear. You can watch the effect of these whispers in the attraction between objects that carry no charge at all. Molecules that should feel nothing for one another still develop a faint pull at short range because the restless field stirs their electrons and makes momentary dipoles that mirror each other for an instant. This is the deep reason London dispersion forces exist, and it is why geckos can stick to smooth walls, and why many materials condense and hold together, even when simple pictures of bonding would say they should not. The pull is small, but it is everywhere, and it would not exist without fluctuations in the background that never quite die. You can also see the imprint of nothingness in precision machines, where silence is the goal. There are detectors that listen for the faintest tremble of mirrors, miles apart, to hear the ring of distant collisions in the sky. And even when engineers cool the devices as close to absolute zero as technology allows and isolate them from every known rumble, there remains a grain of noise that cannot be starved out. It is the quantum shot noise of light itself and the radiation pressure jitter that comes from the restless baseline of the field at the input. This is not superstition. It is a practical problem that the builders of such detectors learn to fight by reshaping the vacuum at the entrance with special light that has less uncertainty in one property and more in the other, squeezed light in the language of the lab. The improvement is measurable, and it is another way. The not quite empty background shows up as a limit when you try to push beyond what classical intuition says should be quiet. Even in solid matter that you could touch with your hand, the idea that nothing can still carry motion finds a home atoms in a crystal at room temperature jiggle because of heat, and that is expected. But if you drain the heat all the way down until the thermometer almost refused to move, the lattice would not become perfectly still. Instead, each atom would keep a baseline wobble, its zero-point motion and nature being practical. Let's that wobble matter for real consequences. One of the simplest elements, helium refuses to freeze at ordinary pressure, even when you chill it within a breath of the lowest temperature available, and a big part of the reason is that its atoms are so light that their zero-point motion is large enough. To rattle them away from a rigid grid, the ground is restless, and that restlessness shapes what phases of matter can exist. At this point, it is tempting to say that the field sometimes borrows energy and pays it back quickly, and many popular explanations reach for that picture because it is vivid, but you should know the limits of the metaphor. Borrowing suggests a temporary theft that makes a bookkeeper look away. The deeper view is kinder to the rules. Energy is not violated, even for a blink. The ground state simply contains fluctuations, the same way a measured signal can have noise in it. And that noise has a well-defined spectrum. The field is never exactly zero on every scale. It is a quilt of subtle correlations that become visible only when you put in boundaries or objects or detectors that respond to certain patterns. For example, if you place two very flat mirrors very close together, the patterns that will fit between them are different from the patterns that fill the open room outside, and that difference reveals itself as a tiny pressure that pushes the plates together. Think about that for a moment, a force from what looks like empty air, the energy did not appear for free. The geometry changed the allowed rumble in the field, and nature balances the books with a force that is now measured and used to calibrate instruments. In clean rooms across the world, the moral is not that you can get power from nowhere, but that the structure of nothingness has consequences when you shape it. The same moral protects us from myths about infinite fuel. It is normal to ask whether these fluctuations could be harnessed as a perfect battery, and the answer is no. The ground state is the state with the least usable energy, and to pull work from it, you must give it a structure that lifts one part of it above another. And then you are the one who paid the bill. Devices that claim to tap vacuum energy without putting in comparable structure or energy always fail when tested because a battery must begin with a difference, and the lowest state by definition offers none. You can only create differences by changing boundaries or materials or motion, and then the energy you retrieve is the energy you invested in making that difference, shaped by the rules of the field. There is one more thread that makes this topic so provocative, and it explains why you will keep hearing about it in modern cosmology if a simple calculation is done, and every mode of the field down to a very fine scale is included. The total energy density of the ground looks enormous, whereas the measured cosmic push that we attribute to dark energy is very small and non-zero. We do not yet have a complete mathematical bridge between these two numbers, and this mismatch is one of the sharpest puzzles in fundamental physics today. It is not a license for fantasy. It is a sign that our best ideas work astonishingly well in their domains, and yet still leave a seam. We do not understand at the join. You will meet this puzzle again when you ask what is stretching the universe. But for our purposes here, it is enough to see that the question grows from the same quiet fact. The background is not empty, so it can drive behavior that would otherwise be impossible. If you let all of this settle, you end up with a calmer picture than the headline phrase, "Energy from nothing might suggest the vacuum is not a void. It is a living foundation with a minimum softness that cannot be pressed to absolute silence and, while that softness never breaks the accounting of energy, it constantly guides the details of how the world behaves. It shifts the colors of atoms. It lets neutral objects attract it, sets the noise floor in our most delicate instruments, and it even decides whether elements choose to freeze or flow at the coldest edge of nature. There is deep romance in that picture, but it is a romance grounded in measurements we can repeat in any well-equipped lab and in technologies that you already carry in your pocket because every photon counter and every quantum-limited sensor has learned to live with the murmur of the ground. So the next time you stand in a dark room and think you are alone, remember that emptiness hums with a lawful whisper, one that never pays out free miracles, yet never stops shaping the universe we wake up in each day. And there is something oddly comforting in that, a sense that the silence beneath everything is not a dead stop, but a gentle breath that sets the tempo for all the music above it. Vacuum that weighs more than matter. The secret of empty space. You grew up thinking that emptiness is the absence of everything, yet the universe keeps a different ledger, where even a perfect blank has weight, and that weight quietly rules the largest scales of reality. So begin with a picture you can hold in your mind, a balloon that keeps swelling, not because you blow more air into it, but because the rubber itself has a built-in pull that urges every patch to stretch a little more, and a little more as time passes. That is what astronomers saw when they looked at the light from certain dying stars that always explode with almost the same brightness. They expected the expansion of space to slow as gravity from matter tried to pull everything back. But the explosions looked dimmer than they should have at their distances, which means space grew more than it would have if matter were the only player. And the simplest explanation is unsettling. The fabric of the universe is filled with a uniform energy that does not dilute as space expands, and the pressure linked to that energy pushes outward rather than pulling inward. So the more space you have, the more of this gentle push you get per total, and the expansion speeds up instead of slowing down. This is not a mathematical trick. It is what the data say across many checks. The explosions of distant stars, the faint grain in the ancient afterglow that covers the sky, and the way galaxies are arranged in ripples on the largest maps all point to the same quiet agent. A background energy that is smooth and persistent, and that behaves in gravity as if it had a pressure below zero. To see why pressure matters, you have to update one idea about gravity. You learned early on, you were taught that mass makes gravity, but in the modern theory of gravity, the source is not only mass, it is the entire budget of energy and pressure and momentum packed into space. A box of hot gas weighs more than a cold one because pressure itself gravitates. Now, imagine a substance whose pressure is negative, a bit like tension in a stretched rope. Tension tries to pull the rope tighter along its length, but when you translate that into the language of space, it acts as a kind of anti-gravity, in the sense that it drives expansion to speed up. The background energy of empty space has exactly this tension. Like character, its pressure is negative and very close in size to its energy density. So when you add its effect to the large-scale equations of the universe, you get acceleration, not deceleration. And that is precisely what the sky reveals to our telescopes. This strange energy earns an even stranger consequence. As the universe grows, the density of ordinary matter thins, because the same amount of stuff is spread over more volume. The density of light thins even faster, but the energy of the vacuum does not thin at all. Each cubic meter keeps the same amount no matter how large the cosmos becomes. So in the early universe, matter dominated and pulled hard. Then as space grew, the unchanging background slowly took over, and now it sets the tempo, and if nothing about it changes in the future, it will dominate more and more. The reach of our telescopes will shrink as distant galaxies slip beyond a horizon we can never see across, and the night sky will quietly simplify until only the nearest island of stars remains visible. This is not doom. It is a reminder that emptiness is not neutral. It has a say in the fate of everything. You can ask where this background comes from, and honest physics will say that we do not yet know for certain. It could be a true property of empty space itself, a constant term that Einstein once wrote down for different reasons and later called his greatest blunder, even though the modern sky seems to have forgiven him and invited that term back. Or it could be the sign of a very light field that mimics a constant today and might slowly change in the deep future either way. The key idea lands in the same place. The vacuum is not just the stage for matter and light, it contributes to gravity, and it does so in a way that does not care where you stand or where you look. That uniformity matters because it explains two things at once: why the effect is hard to notice inside galaxies, where matter still dominates the local game, and why it shapes the expansion of space as a whole, where its smoothness is exactly the trait that carries weight. If you want a feel for how this leaves fingerprints in measurements, think of 3 records we can play. The first is a yardstick written into the pattern of galaxies, a faint echo of early sound waves that traveled through the young plasma of the universe. When we measure the apparent size of that yardstick at different distances, we get a map of how expansion changed over time, and that map prefers a recent push. The second record is the microwave afterglow from when the universe was a hot fog that light left in all directions and froze in place as a subtle mottled pattern. When you read that pattern, you can infer the total balance of matter and smooth background energy. And the answer again points to a large share in the smooth. Part the third is the brightness of those dying stars, which act as beacons that confirm the story directly, by telling us how distances and expansion relate today. None of these tools cares about our desires. They merely report what the sky already wrote. There are limits to what this energy can do, and it helps to name them. It does not clump into structures the way matter does, so it will never make stars or planets. It does not pull on your body in a way you can feel in a room, because on small scales local gravity from nearby mass, and the forces inside matter are far stronger. It does not offer free power plants, because a uniform sea with no differences cannot do work unless you create differences, and then you have paid the bill yourself. And while poets enjoy calling it a cosmic repulsion, it is better to call it a different sign in the bookkeeping of gravity, because the underlying theory treats it with the same sober rules as everything else. Energy and pressure curve space, and this particular combination curves it in a way that makes expansion speed up. The human part of the story arrives when you let it sink in, that the largest driver of the future may be a feature of nothingness. Rather than the glitter of things, it is tempting to believe that reality is made only of what you can gather in your hands. Yet the sky keeps telling you that what you do not see may weigh more than what you do. The empty rooms between galaxies carry a steady influence that does not tire, and you live in its tide. Your bones are built in a galaxy that formed, in a universe where matter once led the dance, and your lifetime unfolds in a cosmos where the quiet background now conducts the orchestra. There is a lesson in humility, here an invitation to trust measurements over intuition and to accept that silence can set the rhythm as much as sound, and perhaps there is comfort too, because the idea that emptiness has a nature takes away a little of the coldness from the word void. The vacuum is not a dead stop. It is a gentle field that gives the universe direction without shouting, and it is a reminder that sometimes the most powerful actors are the ones you only notice when you step back and watch the whole stage. Black holes that erase information, and why physics says they can't. You are told that a black hole is a perfect destroyer, a place where light goes silent and secrets go to die. And at first that sounds right, because everything about a black hole is built to hide what falls in. An invisible boundary forms where escape becomes impossible, and from far away all you can measure is a few blunt facts. How heavy it is, how fast it spins, whether it carries electric charge. Nothing else about the star or the book or the planet it swallowed seems to remain. This is the old slogan that black holes have no hair, which means no fine features you could read, so it is natural to worry that information really is erased. But then quantum physics steps in and refuses to let that happen, because at the most basic level, the rules of time say that the full story of a system must be preserved in principle, not necessarily in a way you can read with ease, but preserved in the total state of the world. And if a black hole simply turned a detailed state into a featureless fog that could never be reversed, those rules would break. So the paradox is, born, gravity seems to erase and quantum theory says it cannot. The tension sharpened when Stephen Hawking showed that black holes are not perfectly black after all. When you include quantum effects near the horizon, pairs of quanta can lead to a slow leak of radiation that is almost thermal, like a faint glow from a hot coal, and over a very long time that glow can carry away all the mass until the black hole evaporates. If the glow is exactly thermal, it carries no message about what fell in, so a pure and detailed initial state would become a mixed and bland final haze, which would be a real violation of the basic conservation of information. That is the information problem in its cleanest form. Why do many physicists say the eraser cannot win? Because quantum mechanics has passed every laboratory test we can throw at it. And because we have strong clues that the right description of gravity at deep scales keeps that bookkeeping intact, the area of a black hole horizon behaves like entropy, a measure of how many internal configurations are possible. And that area grows when things fall in, which hints that what looks simple on the outside hides an enormous number of microscopic states on the boundary. From that seed grew the holographic idea that a region of space can be fully described by information stored on a lower dimensional surface that encloses it, not a drawing on a literal plate, but an accounting rule that treats the surface as the place where the degrees of freedom live, and in certain precise setups we can make this idea sharp. A gravity world in a curved space is equivalent to a quantum theory without gravity that lives on its edge. And that edge theory is perfectly unitary, which is a fancy way of saying it does not forget. So if the edge keeps the story, the bulk with a black hole must keep it as well. That still leaves a practical question that you can phrase without jargon. If information is not erased, where is it? And how would it get out? The current best picture says it is hidden in correlations, not in single particles, but in the way many quanta fit together, early in the life of an evaporating black hole. The outgoing radiation looks very close to random on its own, and the hole keeps most of the record. Later, after enough radiation has left, new quanta can be entangled with the earlier glow, rather than with bits that remain inside. Gradually, the balance shifts, and the radiation as a whole begins to purify. A simple curve that tracks how mixed. The radiation should rise at first, and then fall again as information comes back out. That shape is called the Page curve, and recent calculations that let gravity fluctuate in the right way reproduce that behavior. They do it by finding that certain regions outside the horizon must be counted as part of the effective interior. For the purpose of entropy, which sounds strange, but delivers the necessary drop at late times, translating the math into plain language. The evaporation process can in principle return the hidden details to the universe, not quickly, and not in a code you or I could read, but without violating the rule that the full quantum state keeps its memory. This raises another natural question. Could anyone actually decode a message from a real black hole? For star-sized holes, the time to evaporate is far longer than the age of the universe. So the short answer is no. The long answer is that nature sets two shields, a time shield and a complexity shield. You must wait long enough for the hole to pass the point where it has radiated about half of its entropy, and then you would need to sift a storm of faint quanta and process correlations that are unimaginably subtle. Even if the laws allow it, the task is beyond any machine we can build, which is why physicists talk about what is possible in principle, while knowing it is not possible in practice for astronomical holes. Even so, this principle matters because it protects the coherence of the rest of physics. It tells you that black holes are not cosmic shredders but extreme mixers. They take your detailed input and scramble it almost perfectly across their degrees of freedom, then slowly release it back as a pattern in the outgoing glow. A pattern so fine that a local detector sees only heat. While the universe as a whole keeps the account balanced, this also fits with another stream of ideas that treat the horizon as a very busy place when seen from outside. A stretched membrane with real physical degrees of freedom that absorb, thermalize, and re-emit information in a way that no single observer can catch violating rules. From inside, an infalling observer notices nothing special at the horizon, while an outside observer can replace the interior by this active surface. The two stories cannot be compared by one person, which avoids direct contradictions. Not every puzzle is solved. There are arguments that try to force a break between a gentle interior and a perfect exterior ledger, which leads to the firewall problem, a proposal that the interior becomes violent at late times to save purity. Other ideas try to add soft hair to the horizon, delicate labels that carry extra information through conserved charges tied to the way space remembers the passage of radiation. And there are still debates about how to phrase the evaporation in a way that makes cause and effect completely transparent. But the tide of evidence from theory points away from erasure and toward preservation. Whenever we can replace the black hole with a better studied quantum system that also scrambles and radiates, we find the same lesson. The output looks thermal, in small pieces, yet the global state is pure. It is worth pausing to separate science from myth. Black holes do not let you break the speed of light. They do not give shortcuts to other times in any way we can test. They do not destroy the laws of physics. They stress those laws until the laws reveal their deeper form. The very fact that we can predict the mass and spin of black holes from the ringing tones heard by gravitational wave detectors shows that the classical picture works beautifully on the outside. None of that tells you what happens at the exact center where densities push beyond our current theory. But the information story lives at the horizon and in the long, slow glow, not at the core. And the horizon physics is where we now see a consistent way to keep the cosmic records safe. So the headline is bold, but the ending is calmer. A black hole can look like a forgetting machine if you focus on one small part of the picture at a time. Yet when you step back and count everything, information is not erased. It is hidden, scrambled, delayed, and then returned in principle. The accounting is exact. Even if no one can do the audit, and that is a deeper kind of reassurance, the universe does not throw away its notes. It writes them in a language of correlations that is too rich for us to read, and the lesson for you is the same as it has been throughout this journey. Trust the measurements, trust the conservation laws that have never failed us, and let the mystery be a teacher rather than a ghost. A reminder that the places we thought were endings are often the most patient forms of storage that nature has. Stars that collapse into infinity and still bend time. You think of stars as steady fires, and then one night the story changes because the heaviest stars are not candles but engines that run out of fuel in a very specific way, and when they do, the fall inward writes a lesson about time itself. So begin in the calm years when a massive star balances two fierce forces, the outward push from nuclear reactions and the inward pull of its own gravity, as long as the core can fuse lighter elements into heavier ones. It pays the pressure bill and the star holds its shape, but there is a last step that pays nothing when the core becomes mostly iron. The arithmetic of fusion turns cruel since iron will not give back energy by fusing, and the moment the core crosses a critical mass, the support fails, and the interior caves in almost all at once in a heartbeat. The distance between atomic nuclei vanishes, electrons are forced into protons, and the core turns neutron-rich, while a flood of neutrinos carries away more energy than the final flash of light ever will. What happens next decides the remnant. Sometimes the outer layers rebound and explode while the core stops its fall as a neutron star, and sometimes the collapse, tears past every known pressure, and keeps going toward a horizon that hides an interior from the outside world. But in either case, you learn that gravity can squeeze matter to densities where everyday words become metaphors, and you learn that time is not a separate stage but part of the thing being bent. If the core stops as a neutron star, you are left with a sphere only as wide as a small city, yet weighing more than the sun. The surface gravity is so intense that a pebble dropped from a small height would strike with the energy of a bomb, and light trying to climb away leaves with a lower color than it had when it started. This is gravitational redshift, which is a calm way of saying time runs differently near that surface. Clocks slow down compared with clocks far away, and you can measure this with the pulses of radio waves that some neutron stars emit like perfect lighthouses. Each tick is a rotation of the star, and those ticks let astronomers read the slow dance of time in strong gravity. They see the signal arrive earlier or later, depending on where the companion in a tight orbit sits, and the delay reveals that space-time itself is curved by mass. There is another subtle twist when a compact star spins. It drags the fabric of space-time around with it. This frame dragging changes the orbits of nearby matter and the axes of gyroscopes. And in binary systems, the whole ellipse of the orbit slowly swivels under the influence of the deep. Well, these are not ideas in a book. These are numbers on a screen taken from years of patient timing where a collapsed star becomes a clock in a laboratory. If the fall goes further, the surface recedes behind a one-way frontier, and the outside story becomes even stranger. The collapse is fast in its own frame, but a distant observer never sees the last moment finish. The light from the surface has to climb through an ever deeper well, and it stretches to longer and longer wavelengths until it fades into silence. So from far away, the final approach looks slowed and dimmed, as if time itself were stretching toward infinity. This is not a trick of sight. It is what the equations say, and it is part of why a black hole looks like a frozen shadow to the rest of the universe. Even while the interior continues its fall in peace, nothing you toss in can call back out except for the slow whisper of quantum radiation that very gently cools the whole over spans of time that dwarf the age of the cosmos for the heavy black holes we infer in the hearts of galaxies. In the meantime, the region just outside the horizon is violently creative gas, swirls and heats and launches jets at near light speeds, and gravity bends the paths of photons so strongly that light can orbit once or twice before it escapes, which lets distant telescopes see bright rings that outline the shadow of the whole. What you are looking at in those images is not a surface, but light deflected by an extreme curve in space-time, and that curve is written by a mass that once burned as a star. The link between collapse and time becomes even clearer when two neutron stars, or a neutron star and a small black hole, orbit one another. Their motion sends ripples through space-time that carry energy away, and the pair slowly spirals inward. This has been tracked with exquisite precision. The orbital period shrinks by exactly the right amount year after year, and when two such objects finally meet, the universe rings across space with a brief passing tone that detectors on Earth can hear, and sometimes a flash of new matter is forged in the debris that follows a kilonova, that makes elements like gold and platinum, which means the jewelry on a human hand owes its atoms to the death and merger of collapsed stars, and the signals we receive in light and in space-time together confirm that time and gravity are partners, not rivals. The more extreme the gravity, the more the tempo of time changes, and the more clearly we can test the rules. There are practical lessons hidden in the drama. A neutron star proves that the familiar building blocks of atoms have a second life under pressure. Electrons do not vanish. They are folded into neutrons, and those neutrons pack into a quantum fluid that resists further squeeze with a pressure that comes from the rules of identity rather than from heat, while every white dwarf and neutron star follows a mass limit. Set by those rules, there is a ceiling to what electron pressure can hold, and a higher ceiling to what neutron pressure can hold beyond that ceiling. Gravity wins, which is why some stars stop as white dwarfs, some as neutron stars, and the largest tip into black holes at each step, time behaves differently, and we can read those differences. The surface of a white dwarf shows a modest redshift, a neutron star shows a strong one, and the edge of a black hole shows an infinite one from the outside view. The hierarchy is a quiet map of how matter and time are tied together. You do not need math to feel the last meaning. This gives your night sky. A star is not only a lamp, it is a promise that space-time can be written in many textures, and that endings are also beginnings. The core of a collapsed star becomes a clock, a beacon, a factory, a lens, and a teacher. It bends the path of light and the flow of time in ways that let us check the deepest ideas we have, and each verification makes the world a little more intimate. It says the same physics that slows a clock in a tower by a tiny fraction near sea level is the physics that slows a lighthouse tick near a neutron star by a noticeable amount, and is the physics that freezes the last light from a collapsing surface as it reaches for the horizon when you stand outside at night and feel the old warmth of starlight on your face. You are also feeling the shape of time carved by mass. And when you learn that a star that fell in on itself can still bend the moments of the universe around it, you realize that gravity does not simply pull its sculpts, and that the cosmos is not a stage where time flows undisturbed, but a living fabric where the tempo and the tune are set by the weight of things. Radiation that escapes the unescapable, Hawking's paradox. You might think that a place designed to keep everything in would have nothing to say to the outside world, and yet the deepest prediction of modern physics is that a black hole whispers, and in that whisper hides a shock for common sense. Because classically, the event horizon is a one-way coast road that lets ships sail inward but never return. While quantum theory insists that the very notion of empty depends on who is doing the looking, and on how violently space-time is curved around them. So if you stand infinitely far away from a massive collapsed object and ask what the vacuum looks like, the answer is not perfect silence, but a faint, warm glow that drifts outward, as if the whole had a temperature and a voice. This is the heart of Hawking's insight, and it begins not with a Hollywood picture of particles being born in pairs and one falling in while the other escapes. Although that picture can help your intuition, it begins with a more honest statement about fields in curved space-time, that the vibrations we call modes are stretched and mixed as they travel near a horizon, and what one observer labels nothing another observer can count as real quanta. The calculation is cold and conservative, and it says the outgoing radiation is almost thermal, which is another way of saying it looks like heat, and that heat must come from somewhere, which means the black hole slowly loses mass to pay for it. The scale of the effect sets expectations straight, because the temperature is not some dramatic blaze. It is tiny for large holes. The heavier the hole, the colder the glow. A hole with the mass of the sun would have a temperature so far below the winter of interstellar space that the surrounding universe actually warms it, rather than the other way around, so you will not see stellar black holes boiling away in a hurry. By contrast, a small hole would be hotter and would radiate faster, and, as it loses mass, it would heat up further, accelerating the process, until the last stages would be a burst of energetic quanta in a final flash. If such tiny primordial holes were born in the early universe, some might be finishing their lives today, and astronomers have searched for the telltale gamma rays without a convincing detection, which lets us set limits on how many of those relics could exist. It helps to know that the spectrum is not a perfect blackbody curve. The space-time outside the hole acts like a complex filter that partially reflects some of the outward-going vibrations and lets others through, so the radiation is shaped by so-called grey body factors, and it carries all the familiar species. The hole can emit any field that is allowed to exist in nature: photons, neutrinos, and in the late hot stages, heavier particles as well. The important part for you is simpler. The energy of this radiation is paid from the mass of the black hole. There is no cheating and no free energy machine. The hole shrinks by exactly the right amount for the glow it sends away. You might now ask the honest experimental question if the effect is real. Where is the evidence? And the answer is that we do not yet have a direct sighting from an astrophysical black hole for the reasons above. Their temperatures are far below. The 2.7-degree afterglow that fills space and any feeble Hawking glow would drown in that bath, but we can test the underlying logic in a different way, by building systems where an effective horizon appears for waves in a medium and then asking if those horizons radiate with a thermal spectrum. These analog experiments have been done in flowing water with surface waves in optical fibers, where light pulses create moving refractive boundaries, and in chilled atomic gases where sound like ripples see a sonic horizon. These are not toys. They produce radiation with the predicted temperature set by the gradient of the flow at the horizon. And they strengthen the case that horizons generically radiate, not because of details of gravity, but because of the way fields respond to one-way boundaries. The laboratory does not replace the sky, but it shows that the mathematics is not fooling us. The moment you accept that black holes have a temperature, you are forced to upgrade another grand story, because long before Hawking, people noticed that the equations governing horizons looked eerily like the laws of thermodynamics. Horizons had a kind of area that never decreased, which felt like entropy, and surface gravity that behaved like temperature. But it was a beautiful analogy without a measured thermometer. Hawking radiation changes the analogy into identity. Black holes truly are thermal objects, and the area really is a measure of entropy. And the second law of thermodynamics survives in a generalized form. The sum of ordinary entropy outside plus the area term never goes down. This has practical bite when matter falls. In the area grows by the right amount to pay for the disorder you lost. From the outside view, when radiation escapes, the area shrinks, but the entropy carried by the outgoing glow compensates perfectly. The cosmic ledger stays balanced. There is a famous worry tangled with this discovery, and you may have heard it expressed as a paradox: if the glow is thermal, then where did the details of what fell in go? We will not retell that full debate here, because our focus is the radiation itself, rather than the bookkeeping of information. But it is worth noting a grounded point. This apparent featureless heat is what any local detector would see, while the full state of the radiation across space can be much richer than any small piece reveals, and modern calculations that treat gravity and quantum entanglement with more care suggest that the total output need not be featureless in the long run, even if any tiny sample looks like boring heat. The deep message for today stands. Either way, horizons radiate, and the unity of quantum theory and gravity demands it. Another honest question is whether this glow matters in the busy environment around real black holes. The answer depends on scale. Near many holes, gas forms a hot disk, and magnetic fields drive jets that spray matter at near light speeds. In such places, ordinary processes flood the region with photons that far outshine the Hawking glow by unimaginable factors. This is why images of bright rings around a shadow are dominated by gas dynamics, not by quantum heat from the horizon. And yet, in the quiet far future, when the background light of the universe fades and matter supply dwindles, the steady loyalty of the horizon to thermodynamics would remain. The whole would continue to trade mass for radiation, very slowly but relentlessly. Mists of quanta would carry away the last heavy anchors of a galaxy piece by patient piece, until nothing remained but their own echoes thrown back into space. You can carry the lesson into your sense of what empty and full mean, because a key step in Hawking's argument is the realization that the vacuum is not an absolute thing when space-time is curved and different observers are separated by horizons. They do not agree on the inventory that counts as nothing. Their definitions mix, and a motionless outside observer finds quanta, where a freely falling observer might find calm. This is not contradiction. It is relativity for quantum fields. It says that particle content is not a universal label, but a relationship between a state and a measurement. And you have already met that idea in gentler form in the Unruh effect, which tells an accelerating detector that even empty space has a temperature. The horizon of a black hole is an extreme case of this insight, and the radiation is the price reality pays to keep all its descriptions consistent. There are myths worth deflating along the way. Hawking radiation does not let anything climb out from inside the horizon. The quanta we see are born effectively outside, in regions where they can still reach infinity. It does not let you mine an endless reservoir of power without cost, because every watt is matched by a loss of mass from the source. It does not permit faster than light messaging, and it does not rely on educated guesses about ultra-short distances. The core of the effect can be derived with wavelengths that are never smaller than the scales where we already trust quantum field theory. In curved spacetime, some refinements of the story explore what happens to modes that were once far shorter by tracing them back through the extreme redshift that the horizon produces. But the final answers for the spectrum do not depend on unknown physics. At impossible energies, they rest on principles tested in many arenas. All of this changes the way a black hole feels in your imagination. It stops being a mute devourer and becomes a very slow kind of star that converts mass into a sea of very soft light and neutrinos and other quanta with a power output set, not by fusion, but by geometry and quantum rules. It also answers an old discomfort in the classical picture, where a horizon could have an area that behaves like entropy and a surface gravity that behaves like temperature without any genuine thermometer. Hawking gave us that thermometer, and in doing so wove together the language of horizons thermodynamics and quantum theory into one story that has held up under every theoretical stress test. We know how to apply. The sky has not yet shown us the glow directly, but that is a matter of scale, not of principle. And while we wait for either a tiny ancient hole to pop or a clever indirect signature to emerge, the paradox becomes less a ghost that haunts physics and more a disciplined teacher. It tells you that even the darkest places in the universe are not outside the reach of its deepest laws, and that the line we drew between silence and speech was only ever a line in our heads. Galaxies that race faster than light, without breaking relativity. You are told that nothing outruns light, and then a telescope shows galaxies whose separation from us grows faster than light, and the contradiction is only apparent because the rule that limits speed applies to motion through space, while these galaxies are not sprinting through space at impossible speed. They are being carried apart by the stretching of space itself. So begin with a picture you can feel in your body. You stand on a moving walkway that speeds up the farther from you it gets. If a friend far ahead tosses a ball back to you, the belt beneath the ball can carry it away faster than the ball can roll across the belt. Yet the ball still moves locally at an ordinary pace and never breaks any rule. Now imagine the walkway is the geometry of the universe and the ball is a photon. The farther a galaxy is, the faster the expanding geometry carries it away. And beyond a great enough distance, the recession rate is greater than the speed of light. This is what the simplest law of cosmic expansion says. The more distant the galaxy, the greater its recession speed. And that rule comes not from a force that pushes on galaxies, but from the scale of the map itself changing with time. Like zooming out on a digital map so that fixed dots drift apart on your screen though. None of the dots slide across the screen by their own power. Special relativity polices local motion and every galaxy obeys it. In its neighborhood, stars orbit their galaxies below the limit planet's circle. Stars below the limit, gas swirls and collides below the limit. But on the vast canvas between clusters, space can grow in a way that adds distance everywhere at once. And that addition can outpace light across huge spans without any object breaking the local speed law. You can see the fingerprints of this process in the color of ancient light, because as a photon crosses growing space, its wavelength is stretched like a spring that is being pulled wider. The result is a reddening not caused by the usual Doppler effect of a siren rushing away, but by the fabric itself changing under the photon. A tiny change for nearby galaxies and a dramatic one for the oldest light. We can see the afterglow from when the cosmos was a hot mist began, as radiation with the energy of a glowing furnace, and arrives today as a cold bath of microwaves that fills the sky. The expansion slowed the clock of that light as well. A distant supernova flickers in slow motion, its rise and fall stretched by exactly the same factor. as its red color and that measured time stretch is one of the cleanest pieces of evidence that it is the map that changes, not the bulbs that drift across the map. If a distant galaxy is being carried away faster than light right now, you may ask how we can ever see it at all. The answer is that the walkway does not keep a single speed through all history in the young universe. Gravity from matter made the growth rate drop with time and the sphere around us, where recession equals light speed. The Hubble sphere grew as well. Light that was once stranded on a part of the walkway that ran too fast could later find itself on a gentler part and begin to make headway toward us. A second helpful idea is that we see those galaxies not as they are now, but as they were when the photons began their journey. Many of the small smudges in deep images were much closer and receding more slowly when they launched the light we detect today. By the time those photons reach us, the galaxies that emitted them have been carried far beyond the point where a new photon could still catch us. There is no rule that says the light travel distance must equal how far away the source is now, in fact. For very distant objects, the distance now can be far larger than the age of the universe, times the speed of light, because the stage expanded while the photon was en route. At some distance, a deeper limit appears, an event horizon, not a wall in space, but a boundary in time. Anything that is beyond this horizon today can never send a signal that reaches our future, no matter how long we wait, because the walkway will. Never slow enough for new photons from there to cross the remaining sea. This is a different limit from the Hubble sphere, which is only the place where recession currently matches light speed. The event horizon is about what is possible ever, and it slices the universe into a region that can share messages with us and a region that is forever silent. This boundary is not close. It lies far beyond the realm of galaxies we can visit. But it matters because it tells us that faster than light, recession is not just allowed, it has consequences for what can ever be known. The same picture explains why the expansion does not pull apart everything smaller than a cluster. The walkway adds distance uniformly, but local gravity can grip and hold on the Milky Way, and the Andromeda Galaxy are on a slow collision course. Right now, even though the wider universe expands because their mutual pull dominates over the gentle stretch. Present on that small scale, the solar system is even more strongly bound, which is why your year does not lengthen as the cosmos grows, and why your coffee cup stays the size it is. You live in a structure that decoupled from the flow, because its own gravity or other forces glued it together early on. Cosmic expansion is a background change, not a local wind. Observers have learned to read this story directly from the sky. The pattern of galaxy redshifts lines up with distance in a way that reveals the rate of expansion nearby with one value, and deep in the past with another, a delayed conclusion that expansion once slowed and now has begun to speed up, for reasons linked to the energy of empty space. But do not let that future-facing detail distract you from the core lesson of today. Even without any late-time push, the basic geometry already permits recession faster than light at great distances, because what increases is not the motion of galaxies through a stationary emptiness, it is the size of emptiness itself. Another way to say it is that the speed limit of relativity is a local rule tied to the single small region where you can build a ruler and a clock and compare your motion to your neighbors. None of us can lay a ruler across 1 billion light years and speak of a single shared velocity in the same way. There are common confusions worth clearing away. You may have seen talk of jets from black holes that appear to move faster than light across the sky. Those are illusions caused by geometry and timing, as bright knots race almost directly toward us close to light speed. Their sideways progress seems too fast. When projected on the sky, faster than light, recession is different. It is not an illusion. It is a real growth of distance, and it applies only to very remote scales where no one tries. To define a single velocity across the entire span, you may also worry about messages. Can a super-distant civilization shout loudly enough to be heard if it sits beyond the event horizon? The answer is no. Not because it breaks a rule, but because the rule of geometry says the path for light never in fact crosses into our reachable future. Closer than that, the answer depends on when the light was launched and how the growth of the walkway changed between then and now. The beauty of this topic is that it replaces a supposed law, breaking with a larger harmony. The universe keeps faith with the speed limit in every local interaction, even as its own stage expands in a way that creates separations faster than that. Limit Your Intuition was trained on rooms and roads where the map is fixed, so it takes a while to feel at home on a map that resizes itself while you travel. Once you do, the puzzle softens. A rushing galaxy does not outrun its own light. It is simply carried on a swelling sea, and the sea is what writes the distance when you step outside at night and think about the faintest galaxies in the deepest images. You can know that some of them are already unreachable now, even though their light is just arriving, and that knowledge is not sad. It is a quiet invitation to humility. The cosmos is larger than any boat we could ever sail, and yet it follows rules that are simple. Once you learn which questions to ask about local speeds. When you measure engines, ask about changing geometry. When you measure the universe, and the headline that once sounded like a violation becomes a doorway to a truer idea of space and time. Time that runs at different speeds, depending on where you stand. You grow up thinking time is a single drum that keeps the same beat for everyone, and then you climb a mountain and learn that the drum quietly changes tempo, because where you stand reshapes how fast moments pass. So begin with a picture as simple as a beam of light tossed across a room while you ride an elevator. If the lift rises, the beam that crosses the cabin seems to curve downward. And if the lift falls, it seems to curve upward. The point is not the curve itself, but the clue it gives you that gravity and acceleration are two faces of one experience, and that what counts as a steady rhythm for one observer need not be steady for another. From this seed comes a brave idea. Time is not a rigid scaffold that floats above the world. It is woven into the same fabric as space, and mass can stretch that fabric so clocks near heavy bodies tick a little slower than clocks farther away. The effect is small in daily life, yet it is relentless and measurable, and the history of the last century is full of clever ways we proved it. The earliest tests used light as a clock, since color is simply the ticking of a wave when light climbs out of a gravitational. Well, it gives up some of its energy, and its color slides toward the red, which is the same as saying its tick slows. In the 1960s, physicists sent tiny packets of light up and down a tower and watched that slide happen across a mere handful of floors. Later teams put hyper-precise atoms in boxes and flew them around the world, and found that a clock that spent hours higher in the thin air gained time compared with a twin at sea level, just as the theory predicted even without airplanes. We can watch the effect in quiet rooms today. The most refined optical lattice clocks can register the change in rate between two devices separated by less than the height of a coffee mug. Place one on a shelf above the other, and the higher one runs imperceptibly faster. If you stand between them and listen, you will not hear a difference. Yet the difference is there, and it accumulates. Everyone ages at a rate that depends on the paths they have taken and the places they have lived. And this is not a poetic flourish. It is a bookkeeping rule of the universe that ties experience to geometry. The effect does not stop at laboratories. It makes your phone navigate your city, because satellites that tell you where you are carry atomic clocks that float high above the ground. Their clocks run faster than the ones on Earth, both because they feel less gravity and because they are moving swiftly across the sky. That motion would make them run slow compared with us, while the weaker pull would make them run fast compared with us, and both influences are present. At once, engineers must correct for both every moment, and the fact that your map snaps into place is a daily confirmation that time is elastic. The corrections are not footnotes. They are the difference between a wandering blue dot and a working route. Your morning commute only works because the satellites live in a world where time keeps a slightly different pace. When gravity is extreme, the differences become dramatic. A clock sitting near the surface of a compact star falls behind a clock far from it by a factor that you can measure in the color of the star itself. The spectral lines from matter on the surface arrive shifted compared with the same lines in a laboratory. And this redshift is not a sign of motion alone. It is a sign that the light had to climb out of a deep well and that climb took a toll on its tick. There are even places where light can circle again and again before escaping, and in such neighborhoods, time for a hovering observer drags in a way that would make any familiar schedule useless. You do not need to visit those extremes to feel the logic. However, the same rule that slows a lighthouse clock near a dense star also slows a benchtop clock in a basement compared with one on an upper floor. The same rule that redshifts photons, leaving a heavy surface, also nudges the color of light that climbs from a valley. To a mountain pass, nature is consistent across scales. It simply hides the strongest lessons far away while leaving soft versions close to hand. It helps to understand what really controls the pace. It is not the local strength of the gravitational pull that marks the rate so much as the depth of the well. You are in a person standing in a mine feels the same weight on their shoes as a person on a plateau if both are at the same altitude, but the one who lives deeper in the well will age a shade more slowly because more energy is required to climb out of that position, and in the language of clocks that cost shows up as a slower rhythm. This is why time at sea level and time in a mountain town differ. Even if both feel the same tug on a spring scale across a year, the difference amounts to a handful of nanoseconds, which is so tiny that only a careful instrument can see it across a lifetime. It still amounts to less than the blink of an eye. Yet the point is not personal gain, it is the character of the world. It is the discovery that there is no universal now that stretches across the planet or across the cosmos. There is only the story your own clock writes as it moves through the landscape of gravity and motion. You can test this truth with simple thought experiments that hint at the deeper mathematics picture. Two friends who started life together and then parted, one stayed by the sea and one spent a career working at an observatory high in the mountains. They meet decades later and compare the beating of their best clocks. There is no trick when the devices are brought side by side. The mountain clock stands a little ahead. They both lived honest days. The mountain time simply accumulated faster. You can turn the story around as well and send one friend around the world in a fast aircraft while the other stays home, and you will again find that the moving clock has lost a little time to motion while perhaps gaining a little to altitude. And if you choose the flight path and the schedule with care, you can make the overall result a gain or a loss. The outcome is not arbitrary. The sums always match the rules you can compute, and those rules have been checked with every tool we can build. People often ask what this means for everyday life. It means that anywhere you need synchrony at very high precision, you must carry the curvature of space-time into your design. It means that trading signals across a continent or steering a radio dish to catch a passing spacecraft requires you to keep two kinds of time in mind: the rough human kind kept by calendars and wall clocks, and the refined kind that follows the contours of gravity and the paths of motion. If you have ever watched a sports broadcast beamed from a satellite, you have already leaned on a chain of calculations that nudge the timing just enough to hide this flexibility from your eyes. The elegance of modern life is that it wraps deep physics in friendly interfaces, while never changing the physics below. There is also a quiet lesson for how we think about fairness and sameness. We are tempted to say that time is a single shared thing, because that makes life simple, and for most human purposes it is good enough, but nature does not honor our preference. It offers a deeper unity. Instead, a unity in which differences are lawful and coherent and can be predicted and used rather than denied. The fact that two clocks can disagree, honestly, is not a failure, it is a map. And the map tells us that one of the oldest ideas in science, the idea that there is one absolute time ticking behind the scenes, belongs to an earlier chapter. The new chapter is richer and more human because it says your experience is bound to your path. The seconds on your wrist are not a public resource handed down from above. They are the record of the road you have walked and the height at which you have walked it. In the end, the idea that time runs at different speeds is not a threat to common sense. It is an invitation to expand it. It lets you step outside at night and feel the uneven wind of time on your face as you imagine the sea level clock of a harbor, town, and the high clock of a ridge both keeping faith with their own neighborhoods. It lets you look up and know that the whisper-thin difference between your heartbeats and the beats of a satellite above you is the very reason your navigator works. It lets you picture ancient starlight climbing for eons out of wells, so deep that its color and its tempo changed before it reached your eyes. And it grounds all of this in measurements that any community of careful hands could repeat in a basement, a lab, or a mountain dome. Time is still the drum that leads our days. Yet the cosmos writes the sheet music, and where you stand decides the tempo. Twins that grow old differently, the relativity trap. Imagine two birthdays that begin at the same breath and end on different calendars, not because anyone cheated time, but because each twin chose a different road through it. And that is the trap that catches your intuition about sameness. The idea that there is one universal tick that all lives share. Now slow the mind and follow a clean version of the tale. One twin stays on Earth and keeps a quiet routine. The other rides a craft that sprints into deep darkness at a relentless fraction of light speed, coasts, turns, and comes home. They are reunited. They compare watches that never skipped a beat, and they discover that one has lived fewer seconds than the other. Not a metaphor, but a count of heartbeats and memories, a difference that no argument can erase once the two stand side by side. The surface puzzle is symmetry. If motion is relative, then could not each twin call the other the traveler and claim the other should age less? The resolution hides in two connected truths. First, the traveling twin changes velocity to depart and return, which means they do not share a single steady frame of reference with the one who stayed. And second, simultaneity is not universal. What events count as happening at the same time for one traveler do not match the now of the other. During the turnaround, the moving twin's slice of what is happening back on Earth jumps forward in a way that has no analogue for the one who stayed. So when the two clocks are brought back together, the straight road through space-time, which is the stay-at-home path, always accumulates the greatest proper time, while detours that involve high speeds or sharp turns accumulate less. You do not need equations to feel this. Think of time as a personal odometer that adds up along your route. A straight, calm drive gives the largest reading between the same start and finish. A route with hard braking and bursts of speed returns with fewer miles on the meter, even if both trips begin and end at the same crossroads. In our case, the meter is the twin's own clock and the miles are seconds lived. This is not storybook logic. It is a measured fact that has been tested in many forms. Fast particles born in the sky called muons should die before they can reach the ground if we use their rest lifetimes. Yet their clocks run slow in our frame when they plummet toward us at speeds close to light. So many survive in trigger detectors at the surface. In storage rings at laboratories, muons whirl for much longer than they would at rest. A direct sign that motion stretches their life by the exact factor the theory demands. Heavy ions in accelerators show the same effect on internal transitions. And while airplanes and satellites add complications of gravity that we discussed elsewhere, the simple message from speed alone has been verified again and again. Your time depends on your motion through the world, as surely as your distance depends on your route. The hardest part for intuition is the jump in simultaneity. You imagine the traveling twin cruising away, marking a stack of birthdays for the sibling at home, turning around and marking more. And if you draw this with simple schoolroom time where everyone shares the same now, you will tie yourself in knots. The correct picture uses the traveler's own notion of slices of the universe. Each slice is the set of distant events they call now while moving at that speed. When the traveler flips direction, those slices tilt the other way, and the set of distant events labeled now skips forward across years back on Earth. Nothing physically instant happens to the home twin at that moment. It is only a change in bookkeeping from the perspective of the traveler, but it is enough to make the totals line up without contradiction when they meet. What looked symmetric at first is revealed to be asymmetric because only one twin had to swap families of now along the way. You might wonder if the actual push during the turnaround is the cause of the age difference. And the clean answer is that the size of the acceleration matters only in that. It changes the frame and alters the map of simultaneity. You can make the acceleration as gentle and long as you like, or as brief as a rocket permits, as long as the speeds and the route through space-time are the same. The difference in accumulated time will be the same. Experiments with atomic clocks flown on fast planes have seen this in miniature, and precise comparisons on fast-moving satellites extend the lesson. But a beautiful and often overlooked example sits in our particle beams, where the time dilation follows the speed history perfectly without any need to guess how a particular thruster pushed. A practical insight follows from this. If we ever travel to a nearby star at a large fraction of light speed, the crew can experience a voyage that takes only a few years on their onboard clocks, while many more years pass on Earth. The price is not paid in fuel alone, but in the shift of human timelines. Messages will cross gulfs of time as well as space. Homecomings will be reunions across generations, and deep travel will redraw what a lifetime means. The same physics already runs gently in our daily world. An athlete who flies often visits a slightly different future than a gardener who stays in one town, and the difference is far too small to notice without exquisite instruments. Yet it is not zero. Nature keeps a perfect ledger even when the entries are too fine for our eyes. If you still feel a catch in your understanding, try one more picture. Space-time is a landscape where time is the direction that always flows forward, and the geometry is such that the straightest path between the same two events maximizes the time you live. In empty flat space, that path belongs to the twin who does not accelerate. Any detour that swings out and back makes that clock tick fewer times by the reunion. And that remains true whether the detour is a single high-speed arc or a series of gentle loops. The route is everything. The conclusion is quieter than the headline suggests. There is no trick and no loophole. The twins who grow old differently are teaching you that time is not a universal gift handed out in equal portions, but a personal measure of a journey. Your watch is not merely counting the universe's ticks, it is marking the story of your motion through it. And once you accept that, the paradox folds into clarity, a reminder that many of our strongest illusions come from carrying the habits of everyday rooms into the deep rules of the cosmos. The trap was the expectation that sameness must be absolute. The escape is learning that fairness in physics means coherence, not uniformity, and the reward is a gentler sense of reality in which different paths can lead to the same meeting, but not to the same amount of life lived along the way. Clocks that tick slower in gravity, and why you already live it. You expect every clock to be a fair referee, and then you learn that gravity bends even the rules of minutes and seconds so gently that you live inside the effect without noticing. Which is why this story begins on the staircase in your home where nothing dramatic happens, and yet a clock on the top step runs a whisper faster than the same clock on the bottom step, because time itself flows a little more freely as you climb out of Earth's gravitational well and a little more slowly as you go deeper into it. And the difference is not a metaphor, it is a measurable change in rate that careful hands have tracked with instruments fine enough to hear the shift across the height of a coffee mug. So let the idea settle in your mind. Time is not a separate backdrop. It is part of the same fabric that gravity folds. And wherever the fabric is pulled tight, moments stretch. And wherever it is relaxed, moments ease up. And the reason you already live this every day is that the world you have built depends on synchrony at the level of billionths of a second. And nature will not give you that synchrony unless you respect the slope of time. You can feel the reach of this rule without equations, just by looking at the tools that quietly set the tempo of modern life. National time labs keep networks of atomic clocks, and when they compare them to build international atomic time, they do not simply average the ticks, they also correct for height, because a clock that sits higher above the sea level reference runs faster. And if they ignored that simple fact, the official time of the planet would drift into a nonsense that no fiber, link, or radio signal could clean up. So the first proof that you live inside gravitational time dilation is that civil time itself is adjusted for it, in black and white bulletins that keep the world coordinated. The second proof sits above you, in the sky, thousands of kilometers up, where navigation satellites carry atomic clocks that are deliberately offset before launch, because a clock in weaker gravity runs faster, and a clock in swift orbital motion runs slower, and both effects are present at once, so the engineers pre-tune the onboard frequency and then continue to trim it on the ground. In real time, if they did not, your map would wander by kilometers. Each day, your blue dot would stutter and jump, and all the locations stamped. Services that ride on top of that timing, from ride-sharing to freight tracking to emergency response, would start to fail. The quiet miracle is that they do not fail, which means the calculations that bend time on paper are being used now to keep your life in rhythm. The story runs even closer to you than satellites when your phone locks to a nearby tower. The tower is itself locked to a time standard tied to the global system, and modern networks, like 5G, require neighboring base stations to agree on time within tiny windows to steer their beams and share the air. If the network ignored gravity, it would accumulate timing errors that show up as lost data and dropped calls. The power grid relies on the same idea. Protective relays and phasor units compare the phase of electrical waves across counties and countries, and they too lean on satellite time, which is only accurate because gravity's effect on clocks has already been paid, for even financial markets use precise stamps tied to coordinated, universal time to show when an order was placed or a trade executed, and those stamps trace back to clocks and satellites that take relativity into account. So the money that moves across oceans carries a watermark that says time is local to gravity. If you want a plain number, you can hold in your head, climb a mountain by 1 kilometer, and your watch will pull ahead of an identical watch at sea level by roughly 9 nanoseconds each day. That is 9 billionths of a second, and across a year. That adds up to a few microseconds which you will never feel in your bones. Yet your instruments can see it, and when the aim is to align radio dishes on separate continents or guide a spacecraft across the dark, those few microseconds are everything. At the opposite extreme, step into a deep mine, and you live a hair slower because you are deeper in the well. The lullaby is small but constant, and in a lifetime, it adds up to a sliver of a blink. You can push the logic further outward to the International Space Station, where astronauts live higher up, so gravity would let their clocks run a bit fast. But they also race around Earth so quickly that motion slows their clocks and the second effect wins, which means their onboard time falls behind ours. By a small amount each day, this is not folklore. It is calculated and measured, and it closes the loop between the abstract and the ordinary. The newest chapter in this story might be the most beautiful because it turns clocks into altitude sensors. A new generation of optical clocks can detect a change in tick rate for a change in height, smaller than the thickness of your thumb, which means metrology is beginning to measure elevation, not with rulers or satellites alone, but by comparing time itself across 2 sites. This chronometric leveling can map the geopotential surface that defines true sea level with breathtaking detail, and that has consequences for surveying for flood prediction, for how we compare national laboratories, and even for monitoring underground changes when a large aquifer empties or when magma shifts beneath a volcano. The local gravitational potential changes, and with it, the pace of a perfect clock. The day may come when geophysicists carry portable clocks to watch a mountain breathe not by motion, but by time. All of this is the same simple rule spoken in many dialects. A clock in stronger gravity runs slow. A clock in weaker gravity runs fast. And you can translate that into daily life as follows. You already use devices that share time across long distances. You already depend on services that require that shared time to be faithful to within nanoseconds, and those services already correct for the way Earth's mass leans on the flow of moments. You do not have to feel the difference for it to shape your world. It is baked into your navigation, into your communications, into your lights and your markets, and quietly into the way we define what day it is. The lesson worth carrying is not that time is broken, but that it is honest. It keeps perfect accounts that include where you are and what path you take. And once you accept that honesty, you start to see the world more clearly. You see that a town at the top of a pass and a harbor at sea level live under slightly different rhythms, and that this is not unfair, it is reality. You see that the correction a satellite makes is not a special effect. It is the respect we pay to the way the universe actually works. You see that progress in science often means learning to ask a better question. Not how fast is time in the abstract, but how fast is time here for this clock, in this well under this sky. And you might even find the idea calming, because it says the cosmos is consistent from the basement to the mountaintop, from your pocket to the stars, and that the same gentle rule that slows a clock by a few nanoseconds in your home is the rule that keeps a spaceship honest and a city bright. So the next time you climb a hill and your breath quickens, remember that your seconds are also changing. Tempo by a whisper, and that whisper is already written into everything that works. Particles that refuse to be measured. The uncertainty dilemma. You try to pin a particle down the way you might press your finger on a grain of sand, and the grain refuses to hold still. Not because your fingers are clumsy, but because nature does not permit perfect stillness and perfect certainty to live in the same moment. So begin with a picture. You can feel a single slit in a dark screen, and a beam sent through it, one grain at a time, as you tighten the slit to learn position more. Precisely the spots on the far wall spread out more widely. The beam fans into a broad stripe. The better you know where each grain went through, the less you can predict where it will land. This is not a flaw in your equipment. It is a rule in the architecture of waves. A narrow pulse must be made from many ripples running at many different tempos and directions. And when a quantum of matter or light is prepared in a narrow place, its future motion becomes correspondingly uncertain. The old dream of a perfect pin and a perfect arrow fails, because the very act of preparing a sharp position builds a wide range of possible paths that will be revealed when the particle travels. The temptation is to blame measurement itself, as if the particle had exact values that your tools smear. But the modern reading is stricter. There are pairs of properties that cannot be made sharp at the same time, not even in principal position. And motion are the classic pair. There are others as well, like the energy of a state, and the duration over which you can speak of that energy cleanly, or the number of quanta in a field, and the phase that ties them together. These are not quirks of machines. They are sentences written into the grammar of waves and the experiments that chase them. Repeat the same lesson across many platforms. Watch cold atoms in magnetic traps. The more tightly a cloud is confined, the more quickly it leaks into motion. Watch electrons in a narrow channel on a chip. The channel acts like a slit, and the emerging electrons spread in direction. Even in perfect vacuum, watch. A beam of molecules pass through a thin grating and land in a pattern of bright and dim fringes, and then narrow the grating, and note how the pattern widens. The world keeps refusing your demand for exactness, because exactness in one question implies generosity in the other. There is a famous story about trying to look without pushing, and it helps to clear that fog. Imagine a microscope that tries to see a tiny bead. If you use gentle, long wavelength light, you disturb the bead less, but you cannot resolve fine detail. If you use short wavelength light to see more precisely, each photon carries more punch, and you jostle the bead. The deeper insight is that this is not just a nuisance that could be fixed by a better lens. It reflects the same trade that the slit, revealed a narrow view in space, demands a wide spread in momentum of the probing light, and the recoil writes itself into the object. The effort to learn position creates uncertainty in motion. Even if you could make the glass flawless and the table perfectly quiet, the push would remain, because it is not a defect, it is the price that the world charges for knowledge of that kind. The most persuasive evidence that this is a true limit and not a temporary embarrassment comes from systems where we can count everything with exquisite care. Heavy ions in storage rings live longer when they move fast, because their inner clocks are stretched by motion. But when you try to nail down their internal position in a trap, the lines you use to read them broaden in exactly the way that a limited lifetime predicts the time. Energy pair reveals itself that way. The shorter the residence, the broader the color, and this broadening is not a symptom of sloppy gear. It is a shadow cast by the finite time you allow the state to exist. You can see the same logic in small semiconductor dots, where a single electron can sit and then leave. The spectrum of that dot shows a width that tells you about the dwell time, a kind of built-in blur that does not go away when you turn off the lights in the lab. If this sounds like a limit that only annoys measurements, you are missing the deeper gift. The uncertainty rules are part of what makes matter stable. Imagine an electron in a hydrogen atom trying to fall into the nucleus like a pebble into a well. The closer it tries to sit, the more sharply defined its position would be, and the more violently uncertain its motion would become. That uncertainty pumps up the kinetic energy and pushes the electron outward to a cloud with a definite size. The atom is stable, not because the electron orbits like a planet, but because the trade between position and motion finds a compromise at a small and finite radius. Push inward and motion fights back. This same dance sets the scale of chemical bonds, the spread of electrons in molecules, and the glow of heated matter. Your eyes see stars at night because electrons cannot sit perfectly still, and the spread of their motions gives rise to the colors that climb out. The uncertainty dilemma also teaches you how to design better instruments. Not by breaking the rules, but by using them. You can choose to measure one thing gently and let the world punish another thing hard. For example, a device can be built to watch one special combination of position and motion while dumping the back action into the opposite combination, so that over many trials the chosen quantity can be read with less noise than a naive reading would allow. There are experiments where a tiny mirror on a spring is watched by light in such a way that the push from each photon largely adds to motion that the detector then ignores. This is called a quantum non-demolition strategy, and it demonstrates that uncertainty is not a blanket fog that covers everything equally. It is a tilted landscape where skill lets you walk along a ridge at the cost of sliding down a slope. You do not care about that day. And yes, there is a cost. There is always a cost. The point is that the cost is predictable and can be steered. A common confusion is to think that uncertainty can be beaten by hidden information that we simply have not found. Yet people bring up clever pairs of particles that fly apart with connected properties and ask if the link lets us read both sides at once with no penalty. This was the hope behind old arguments about spooky action, but careful experiments that separate the particles by long distances and close every obvious loophole show that while correlations are real, they do not let you extract sharp values for incompatible questions on each particle. At the same time, the pair can be placed in a state where the sum of two distant readings is known perfectly. Yet each local reading remains uncertain in exactly the way the rules demand. The universe is generous with patterns across space, but it remains strict with the price it charges for certainty at one site. You might worry that all of this makes prediction impossible, but the truth is better. The quantum laws give you sharp predictions about distributions and about limits, and they do so with a reliability that has no peer devices designed with these limits in mind. Work at the edge of what is allowed, and they do so day after day. The electron microscope that shows you atoms must accept a minimum blur from diffraction, and still it reveals structures that chemistry depends on the atomic force. Microscope that drags a sharp tip across a surface, finds positions by touch, and dodges the push from light, but it still lives with the trade between gentle probes and clear images. The more carefully you think about what you ask, the cleaner your answers become, and the closer you can come to the boundary without stumbling across it. There is a quiet human lesson in all this as well. A reminder that knowledge always involves a choice, and that some questions barricade others. The best strategy is not to demand everything at once, but to design a sequence of questions that each respects the cost of the last. You already do this in life when you plan an interview or a medical test or a negotiation. You choose what to clarify first, knowing that each answer moves the ground beneath the next. Your mind is a measurement device that must budget disturbance as well as curiosity, and the quantum world simply makes that budgeting exact. In the end, the particles do not refuse you out of spite. They refuse because the fabric that carries them ties sharpness in one place to looseness in another, and because the act of preparing and reading a system is itself a physical event with ripples that cannot be wished away. The dilemma is not a wall, it is a map. It tells you where certainty can live and where it must be paid for. And once you accept that map, you stop asking the world to be simpler than it is, and start asking better questions, the kind that lead to working instruments, stable atoms, durable matter, and a deeper respect for the way reality trades clarity for grace. Events that happen with no order. Quantum's time trick. You are used to stories that run in a line because life trains you to think that first comes cause and then comes effect, and that every pair of events can be sorted into before and after, like books on a shelf. Yet the quantum world offers a quieter and stranger lesson that some tasks can be arranged so that there is no single answer to which came first, and that the lack of order is not chaos, but a resource as clean as a laser and as measurable as a heartbeat. So begin with a simple rule of everyday work. If you must wash a shirt and then dry it, the order matters, and if you reverse the order, the result is foolish. The same is true for many microscopic operations that scientists perform on a fragile particle. One device might give it a certain twist, while another device gives it a different twist, and usually you would send the particle through one box and then the other, and the sequence would be a choice written in ink. Now add a very quantum move. Make the route itself depend on another degree of freedom of the same particle for light. A favorite choice is its polarization, which you can prepare in a superposition that means the routing element that steers. The light makes two paths at once, one that sends the particle through box A, then box B, and another that sends it through box B, then box A. And because the routing is coherent, those two stories do not get mixed. Like coins in a jar, they interfere. Like ripples on a pond, the effect is called a quantum switch, and it creates an indefinite causal order. The experiment is not a rumor. It has been built with photons and with acoustic waves and with microwave pulses on superconducting circuits. To certify that the order really is not fixed, researchers use a test called a causal witness, which is a way of asking whether any classical mixture of definite orders could reproduce the data. And the answer is no, in the proper regime. The results cannot be matched unless you accept that the process does not have a single order. The difference between randomness and indefiniteness is crucial. A random choice would flip between A before B and B before A from trial to trial. But there would be no way for the two possibilities to talk to each other. A quantum superposition is different. The two possibilities are present together, and their phases can add or cancel, which means you can make outcomes that would be impossible if the order were only shuffled. This is why the effect has teeth. You can set up problems where the only way to succeed is to exploit interference between the two orders, and the data then reveals that you did in fact use a resource that a coin flip cannot supply in communication tasks, where two noisy devices sit in your way and you do not know which you will face first. An indefinite order can raise the chance of getting a clean message through, beyond the best that any fixed order allows, in certain kinds of channel discrimination. An indefinite order can help you tell two devices apart with fewer queries in computation like settings. There are algorithms where the number of times you must call black box gates can drop when the order is allowed to float. These are not science fiction claims. They are careful statements that have been proven in limited but real scenarios with machines on lab benches, built by people whose job is to find the loopholes and close them. At this point, your instinct may whisper that the effect must be a form of time travel or a violation of the rule that signals cannot outrun light, but neither is true. Each local operation still happens in a normal way at the place where its box sits. No signal is sent backward through time, and no observer sees a contradiction. The indefinite part lives in the global wiring of the experiment. The route is arranged so that the question which happened first simply has no single answer. This world is more forgiving than our grammar, and it allows a process to be well defined without being forced into a total order. You can think of it like two chefs preparing the same dish, where the key is not who chops first and who stirs second, but that the two sequences are set up to interfere in the final taste. The interference is the certificate that you did something beyond a simple shuffle. You can even see it in a test where the two boxes are chosen to be operations that do not commute, which is to say that swapping their order changes the outcome. In that case, the indefinite order creates patterns at the output that would vanish if you sneaked in a classical draw of the order behind the scenes. There is a deeper curiosity hiding here that reaches beyond the lab. In general relativity, the geometry of space-time decides which events can influence which other events, and that geometry itself is not fixed. It is shaped by matter and energy. Now add the quantum hint that matter can be in superposition, and it becomes natural to ask whether causal structure might also be in superposition. At very small scales, you could imagine a massive object prepared in a superposed position, which would create two slightly different gravitational fields, and hence two slightly different flows of time. A particle interacting with this situation would then live through two different orders of events at once. Although we cannot do this with real gravity, yet we can simulate related ideas in other platforms, and we can explore the mathematics of processes that do not assume a preset order. The point is not to sell a fantasy, but to show a path building from verified tabletop effects toward questions that touch the boundary of quantum gravity. The moral stays cautious and clear. The absence of a fixed order need not mean disorder, and it does not require any violation of deep symmetries. It is simply a new notch in the belt of ways quantum systems can be arranged. It is worth pausing to say what indefinite order does not do. It does not let you decide a fixed order after the fact and retcon the past. It does not give you free computational leaps across all problems, and it does not make cause and effect meaningless. Instead, it widens the design space for machines that manipulate quantum information and for networks that must thread signals through uncertain environments. In fact, the first applications that engineers chase are practical and modest beta metrology that is less sensitive to the drift of devices, better discrimination between similar channels, and more robust protocols for sending a fragile quantum message through a corridor of noise where the walls move. You do not need poetry to see the appeal. Any city with a busy data backbone, any telescope that must stitch light from many stations, any clock comparison that must send signals through clouds of interference can benefit from strategies that do not swear a single order of operations into law. The human lesson rests in how you think about sequence in your own work. Most of us treat order as the backbone of certainty. First plan, then act, then review, and for good reason. But the quantum switch invites a softer mindset that sometimes two ways of acting can be held in play at once, and that the space created by their coexistence produces results that neither order alone can deliver. There is a dignity to that idea, and a warning. As well, the dignity is that you can design questions to which the world will answer in richer ways. If you do not force it into your favorite script, the warning is that our language can blind us when it insists that one of two exclusive labels must be true. The most generous science asks a clearer question, not which came first in an absolute sense, but what pattern of interactions best explains the data in front of me. When you look at the quantum switch with that clarity, the trick stops being a riddle and becomes a tool, a small door into a larger house where time is not a single line, but a fabric that can be folded without tearing, and where events that refuse an order are not rebels, but the workers that make new kinds of order possible. Decisions that rewrite the past. Wheeler's delayed choice. You have always trusted that once a thing has happened, it is locked in place like ink on paper. And then you meet a design so simple it feels like a toy that seems to ask whether your choice in the present can tell a story about the past that was different from what you thought, and that design is Wheeler's delayed choice idea, which invites a single photon into a maze and lets you decide very late whether it should reveal itself as a traveler with a definite path or as a wave that explored both routes at once. So begin with a picture that keeps your feet on the ground. A beam splitter sends one photon into a superposition of two paths. Mirror arms guide those possibilities toward a second region where you may or may not place another beam splitter if you leave that final device out. The two paths reach separate detectors, and the clicks tell you which route the photon took if you slide the second beam splitter in. Very late, the two paths are recombined, and their phases can add or cancel. And now, nearly all clicks appear in one detector. and almost none in the other, an interference outcome, as if the photon had taken both routes and met itself. The twist is, timing, you can decide whether to insert the recombiner after the photon has already passed the first splitter and is well on its way. The results obey a strict pattern. Your late choice determines whether the statistics show path knowledge or interference, and this tempts the imagination to say that the present rewrote the past. But a karma reading keeps the wonder while saving causality. The experiment does not flip what already happened. It changes which descriptions are valid for the entire run. Once you include the measuring devices you actually used in the end, the clean way to feel this is to think about what counts as a record if the apparatus is arranged so that in principle, a trace of which path could survive anywhere, even faintly in a detector or in the environment, the interference is lost, and you see two humps of clicks if the apparatus is arranged so that no path record can exist, and the two routes are made indistinguishable. Then the interference returns, and you see nearly all clicks in a single output. The late choice simply decides which world you built. And the photon plus equipment evolve together into a joint state that already contains the conditions for one pattern or the other. There is no signal sent into yesterday, and no rule that collapses after the fact instead. There is a global consistency. The outcome at the end matches the entire experimental context, including devices you add at the last moment. And this is why researchers use random numbers created, while the photon is in flight, to decide whether to insert the final element, the interference case, and the which path case still fall into their proper bins without contradiction, which is exactly what a theory that links outcomes to the available information predicts. To see how far this idea can stretch, consider Wheeler's cosmic thought experiment. Imagine a quasar far away, whose light is split by the gravity of a massive galaxy into two arcs that reach Earth by different routes an astronomer today can choose. To set up a detector that forms a sharp image of the two arcs, which is like measuring which path, or to set up a device that erases the path difference and looks for interference, which is like sliding in the final beam splitter in the lab. The choice can be made now even though the light began its journey long before there were eyes to watch it. And the results are never paradoxical. If you image the arcs, you have made the paths distinguishable, and you do not see interference. If you arrange things so that no information about the route can exist, you can gather interference fringes from the recombined light. The past is not rewritten. The record was never fixed until a consistent whole experiment was defined, and the sky is patient enough to let you choose which consistency to reveal. A frequent confusion is to imagine that the photon was a tiny marble that chose a corridor long ago and that your late action somehow swapped its history. The better language is different before detection. The quantum state carries possibilities that include both arms and the correlations with the gear you actually use. Decide what patterns can appear at the end in the which path mode. The possible histories are labeled with distinct records, so they cannot add coherently in the interference mode. There is no surviving label to separate the histories, so they can combine and shift the outcome like ripples that meet and either strengthen or cancel each other. Measurement is not a passive glance. It is a physical coupling that either leaves or does not leave a readable trail, and the delayed choice simply keeps that coupling flexible until the last moment. The same logic has been pushed into careful variations with quantum erasers, where auxiliary systems first tag the paths, and then clever operations remove the tag before the final detectors in the sub-ensemble, where the tag is truly erased. The fringes come back, while in the sub-ensemble, where a usable tag remains, the fringes stay gone. And when the tag is only partially removed, you see partial fringes, which is a very concrete way of saying that information and interference trade places. Like two ends of a seesaw, the rule is precise enough that engineers can use it to tune visibility, and which path knowledge like a dial, a fact that turns a philosophical problem into a practical control knob. What should you carry away from all this? Not that your decision in the present reaches back and edits the past, but that quantum events do not have a single story independent of how the world makes that story readable. Your choice at the end selects between two compatible accounts, one in which paths are real and recorded, and one in which paths are not defined and waves add their phases, and the universe refuses to speak in both voices at once. The lesson is deeper than a party trick it is. A blueprint for building machines that guard or reveal information, and it is also a soft instruction for how to ask questions. The better you match your question to the patterns your setup can support, the clearer and cleaner your answer will be, and the less tempted you will be to declare a paradox where there is only honest accounting. The beauty of Wheeler's idea is that it shows how a single photon can carry two kinds of possibility to the very end, and how the world commits only when you let it. The commitment is not retroactive, it is global and consistent, and it mirrors your own life more than you might expect. You do not know a story until the last page is turned. The pages you include and the order you read them in change the meaning without changing the ink, and once the book is complete, the tale makes sense. As a whole, that is how nature keeps faith with causality, while still giving you the power to choose which face of reality you want to bring into focus. And perhaps that is the quiet gift of the delayed choice experiment. It teaches you how to think in wholes rather than fragments, and to see that mystery and clarity are not enemies but partners that take turns depending on what you ask. Worlds that multiply infinitely but never touch each other. What if the world never chooses a single outcome, but keeps every allowed story at once, separated not by distance but by silence? And what if you are not a lone reader of that story, but a character whose lines split whenever nature offers more than one ending? This is the gentle but radical promise of the many worlds idea, born from a simple decision to stop adding an extra rule that says results suddenly snap to one value when you look, and to keep only the smooth evolution that the quantum laws already provide. So begin with a scene you can picture without equations. A tiny system meets a simple detector. The two interact, and instead of one forcing the other to settle, their fates become linked like dance partners who mirror each other. If the system goes left, the detector records left. If it goes right, the detector records right. The linking continues outward to the air, and to the room, and to you, as the reader of the instrument. Very soon, every trace in the environment carries one consistent version of events. And because the environment is a choir of countless singers that never rehearse together, the delicate phases that would let the two possibilities interfere are lost to this sea. Roud. The name for that loss is decoherence, and its effect is swift beyond ordinary imagination. In the blink of an eye, the two versions of the world that could have interfered become two branches that no longer speak, not because a new law forbids it, but because the information that would allow them to meet again has been strewn into degrees of freedom no one can collect, like confetti thrown off a tall balcony into the wind. The striking claim then becomes almost modest. There is no special collapse. There is only branching, and the branching is nothing mystical. It is bookkeeping for correlations that spread. You do not summon new universes with a choice. Rather, the universal state already contains the structure that matches each allowed outcome, and you become correlated with exactly one of those structures. So when you check the dial, you find a single reading, and so does everyone around you. Yet in another branch, a different reading is just as definite for its inhabitants. The worlds multiply not by creating copies of energy, but by parceling the same total description into non-communicating components. And this is why no branch can talk to another or steal from another. The microscopic phases that would enable a reunion have been shared with the environment in patterns that cannot be reversed in any reasonable time. So the worlds never touch, even though they together form the full solution. If you ask for evidence, you will not find a poster that says other branches were visited, but you will find a long record showing that decoherence is real and fast, and that interference is preserved only when a system is fiercely isolated. Trapped ions and cold atoms and superconducting circuits keep coherence long enough to perform controlled dances, and then lose it the instant the B lets the environment back in. Large objects decohere faster, still, because there are more ways to leak information into air, photons and vibrations. This explains why your desk shows a single location and not a blur. It is constantly measured by everything around it without anyone trying. which means the classical-looking world is not a special exception. It is the ordinary appearance of a quantum state that has spread its phases so widely that each macroscopic alternative becomes a self-contained history. Probability, the part that keeps you honest when you predict outcomes, is not thrown away in this view, it is reshaped. You still assign chances to what you will see when you perform an experiment. Because before you look, there are many branches compatible with your setup. The weight you give each branch is guided by the square of its amplitude, and while there are different routes to justify that rule, from decision arguments that ask what a rational agent should bet on to symmetries that show how swapping labels cannot change the accounting, the practical message is simple. Every normal quantum prediction survives. Only the extra postulate of a sudden snap is left behind. There are common worries that deserve clear answers. Does branching make copies of you? The calmer phrasing is that there are now multiple versions of you, each knit to a different record. None is a ghost and none is a fake. Each remembers a single consistent past, because each is entangled with a consistent trail of evidence. Does branching violate the conservation of energy? No. The energy book is balanced in the global state, and the branches are not independent banks printing money. They are parts of one solution that no single observer can hold in full. Could branches ever meet again? In principle, recoherence can happen for tiny systems. When you carefully undo the entangling influences, and physicists have done such reversal for qubits and molecules, but for macroscopic histories, the conditions required are so exacting that the universe will not arrange them by accident or by ordinary engineering. The confetti would have to be gathered piece by piece from every corner of the air and from every photon that wandered away. So for all practical paths, the separation is permanent. The view also offers a sharp lens on quantum computing, while avoiding easy myths. A quantum computer does not let you chat with your other selves. It keeps coherent superpositions within one device, so that multiple computational paths can interfere in a way that amplifies good answers and cancels bad ones. As soon as you measure, the device branches, and you read a single outcome. The advantage comes not from seeing every branch, but from designing the calculation so that the structure of many branches pushes probability onto correct results before the machine is allowed to decohere. When decoherence wins early, the advantage evaporates, which is why the field is a race to shield qubits from the world. The philosophy is heavy, but it need not be dark. Many worlds does not turn your life into a stack of disconnected fates. It reminds you that certainty is local and earned. It says that what you experience is one consistent strand through a larger tapestry, and that the fabric is richer than your strand alone. It removes a sudden magical rule and replaces it with a single continuous story, and it gives you a way to understand why macroscopic reality feels stable, while the microscopic world remains a sea of possibilities. The stability is not denial. It is the result of relentless sharing of information with the environment that entombs alternatives in separate records. You are free to prefer other interpretations that add a special snap or hidden instructions. Science allows that taste, because all of the contenders agree on the outcomes of experiments within their shared domain. But the many worlds idea has a calm kind of audacity. It takes the equations at face value, it lets the world keep all the paths it can support. And it asks you to accept that never touching does not mean never existing. So when you stand at a window at night and think about how a single decision can change a life, carry this quieter thought too, that the universe may not throw away unused possibilities at all. It may file them in a library of branches that you will never visit, and that will never visit you. And it may be in that silent library that the full honesty of quantum theory lives, not as a threat to meaning, but as a patient invitation to widen your sense of reality, without losing your footing in the one story you can read. Fields that replace particles and make reality ripple. Suppose you were never made of little pellets at all, but of something smoother that fills every corner of space and time. And suppose what you call a particle is only a brief crease in that smoothness, a traveling knot the way a pulse runs along a rope without the rope itself going anywhere. Then the world changes tone at once, because the basic thing is a field, and the click you hear in a detector is a ripple reaching you with just enough energy to leave a mark. So begin gently with a picture you can hold. Imagine an ocean that extends everywhere. At each point, the water can be higher or lower, and it can sway in time. A small lift that moves outward is a wave. And if you stand with a cup, you can catch exactly one gulp of that moving swell. In physics, the ocean is a field that lives at every point in space. And the gulp is what we call a quantum. The photon is not a marble flying through a void, but a neat packet of the electromagnetic field that carries light. The electron is not a bead, but a ripple in the electron field. Every kind of matter that we have named in our best theory arrives as excitations of its own field, and because all quanta of a given field are made from the same fabric, they are perfectly identical. No sticker can tell one electron from another, since there is only one electron field, and each electron is a crest on its surface. This view fixes a confusion that you may have carried from childhood. You do not need forces that reach across space to pull on distant pellets, because fields live everywhere and talk only to their neighbors. Push on the field here, and your push spreads at a finite speed to the next place, and the next, a graceful fit, with the rule that no influence outruns light. The old idea of action at a distance is replaced by local changes that march outward as ripples, which is why a magnet feels its partner only after a tiny delay, and why sunlight from the Sunday touches Earth 8 minutes late. All of it is the story of a field that was set ringing there, and is now ringing here. Once you accept fields as the actors, familiar mysteries soften into tools. A detector does not smear out a wave because it is clumsy. It clicks because it can only absorb energy in lumps that match the field's natural packets. So light arrives as quanta, even though it travels as a spread in the field. In matter, the same logic explains why there is a lowest energy state, and why you cannot pile an electron into the same place with the same state as another. The structure of the electron field has rules about how many ripples can share a pattern, rules that build the shell structure of atoms and the stability of bulk matter. This is not romantic language, it is the working grammar behind chemistry and the strength of the chair beneath you. The field picture also turns the idea of charge and force into geometry. When you move an electron, you are not throwing a pebble. You are bending the electromagnetic field. That bent field reaches a neighbor and nudges it. For attraction, one field arrangement is favored. For repulsion, another. And buried in this story is a powerful kind of symmetry that says you can change a certain internal phase of the electron field everywhere, and nothing observable changes. To keep that true, the electromagnetic field must respond in a precise way. This is the deep reason the two are tied, and why their interaction has the form it does. We usually meet it as a tidy set of equations, but the heart of it is that a simple freedom in how you label the electron field forces the existence and behavior of the light field that couples to it. Mass, the quiet heaviness that makes things resist acceleration and that lets matter collect into stars, is also a field story. And here the tale adds a surprising calm. There exists a field that does not go to zero, even when left alone. A field that keeps a constant value throughout space, like a thin atmosphere that you cannot feel but that everything moves through. When certain quanta, such as electrons and quarks, interact with this field, they gain inertia. They act as if they have mass. While the photon sails through unaffected and remains massless, the carriers of the weak force do interact and become heavy, which explains why that force has such short reach. You have heard the name of the quantum ripple of that background, the Higgs boson, which we saw at a collider when two streams of ripples met and briefly pushed the field hard enough to ring on its own. The discovery was not only a trophy, but a confirmation that mass can be an interaction rather than a property handed down from outside. Even the idea of antiparticles becomes less spooky in the field view. The single electron field supports ripples that carry negative charge, and also ripples that carry positive charge with matching mass. When the two meet, the energy in their ripples can flow back into other fields, and the pair disappears. And with enough concentrated energy, new pairs can be made. You have seen the fingerprints of this at colliders, where beams of ripples slam together, and the energy in their fields converts into sprays of new quanta, a conversion that obeys strict conservation of charge and momentum, not because an accountant watches, but because the fields can only rearrange their patterns in ways that respect the symmetries they carry, lest this sound only cosmic. The field idea runs the devices on your desk. In a crystal, the positions of atoms define a field of allowed motions, and a collective vibration in that grid is a phonon, a real quantum that carries heat and sound through the solid. A ripple in the spins of those atoms is a magnon. Ripples that couple light and matter in a cavity make polaritons. Engineers catch and guide these quanta the way surfers read swells. That is why lasers are stable and sharp, why superconductors expel magnetic fields and carry current without loss when their paired electrons line up into a single coherent field pattern, and why a thin sheet of carbon can host electrons that move as if they were massless ripples, giving you odd transport properties with ordinary carbon atoms, arranged just so. Evidence for fields is not vague. The way scattering events happen in detectors across the world follows the predictions of quantum field theory to many decimal places. The way the electron wobbles in a magnetic field matches a calculation that includes the nudge from all known fields. And the match is so precise that any new field must either be very heavy or very shy to have escaped notice. The way the weak force twists the behavior of certain decays follows a field model that unifies it with electromagnetism at high energies, and every step that experiment has taken has reinforced that union. We do not cling to the field idea out of taste, but because it keeps being right where money and time are spent to check it. The philosophical temptation that follows is to say that particles are illusions. But it is kinder to say that particles are the right description when the ripples are well separated and short-lived in your detector, while fields are the right description when you want to speak about the whole stage at once. Both pictures are the same play seen from different seats. What matters is to use the one that makes the next question clearer, and the field view often does that, because it organizes your thinking around locality, symmetry, and stability. It tells you why identity is so strict for elementary quanta, why forces have the forms they do, and why the vacuum is not a blank, but a defined state of the fields with a flaw that sets the stage for everything else. There is a gentler human meaning tucked inside this physics. The recognition that you are not a collection of tiny beads in a bag, but a pattern in a set of fields. A moving chord struck on a universal instrument makes identity feel both less brittle and more wondrous. It does not make you less real, it makes you more connected. Every atom in your body is a choreography of ripples, whose rules are shared with the stars. And the very fact that you can taste a berry or listen to a voice is the result of smooth fields that carry signals reliably from one place to another. When you look at sunlight on a wall, you are watching a field that has been ringing since before it left the surface of the sun. When you speak, you send ripples through air and electronics and glass. And when you close your eyes, the quiet you hear is still full of motion, because the instrument never stops humming at a level beneath your senses. To learn that fields replace particles is not to lose the world. It is to learn the deeper reason it holds together, and to understand why reality ripples, and yet remains continuous enough to cradle our lives. Light that can be stopped and stored like memory. Imagine asking a beam of light to wait for you and watching it obey. Not by dimming into nothing, but by sliding to a near standstill, and then pausing inside matter, as if a diary had closed on a half-written sentence. And when you open the diary later, the sentence continues where it left off. To understand how this can be real, you have to trade the picture of light as a wild arrow for a calmer one, in which a pulse is a moving pattern that can be copied into another medium and back again. Because what laboratories do is not trap tiny bullets in a jar, but persuade an atomic crowd to remember the shape and color and timing of a passing flash, and then to hand it back on command. And the trick begins with an idea called transparency created on demand, where a cloud of atoms that would normally absorb a certain color is coaxed by a gentle control beam to become see-through for a second beam that carries the message you care about. At the atomic level, the control beam shuffles the possible ways electrons can respond, so that two paths for absorbing the signal cancel each other, and the medium stops eating the light. Yet the cancellation has a side effect that is the real prize. The response of the atoms changes so sharply near that color that the group speed of the pulse drops by a giant factor, centimeters per second, instead of hundreds of millions of meters each second in the most dramatic cases, which means the crest of the pulse still moves at the cosmic limit. But the envelope that carries information crawls like a careful walker in a crowded room. Now comes the storing. Once the pulse is fully inside the cloud, the control beam is slowly turned down, and the dance that kept the medium transparent fades, in a way that maps the pattern of the light onto a pattern of atomic coherence, a quiet alignment of phases between two long-lived internal states that now hold the memory of the incoming wave. There are no trapped photons sitting inside like peas in a pod. There is a pattern written into the matter that can persist for microseconds in a warm vapor, or for much longer in ultra-cold gases, and in carefully prepared solids where motion is tamed and disorder is low. When the control beam is turned back up, the mapping reverses, and a new pulse emerges that carries the same envelope as the original, the same little wiggles in time that you wrote into it. And when the experiment is tuned with care, even the fragile quantum correlations of a single photon can be preserved well enough to be useful, which is why people call these devices quantum memories for light. The headline surprises are matched by grounded details you can feel. The slower the light travels, the shorter the pulse has to be, to fit inside a finite medium, so groups use short bursts that can be fully contained before they convert them to spin-like memory. The better the isolation from stray bumps, the longer the stored pattern can live, so cold atoms and rare earth crystals inside clean cavities push the timescales out, while vapors at room temperature trade lifetime for simplicity and lower cost. And there is a strict honesty in the bookkeeping. As always, stopping and starting does not violate the speed limit of the universe, because no signal jumps ahead of itself. The information in the pulse never outruns the front edge that sets the causal pace. It simply waits as a matter-based pattern until you ask for it again. This ability to catch and release light is not a parlor trick. It is at the heart of efforts to build long-distance quantum networks, where single photons carry fragile keys that must be stored at relay stations, while partners at the far end are prepared. It lets telescopes and lids on chips line up signals with exquisite timing by buffering a pulse without turning it into an electrical current. It allows metrology tools to sharpen the edges of a pulse and create better filters tuned to a selected color. And it gives teachers a way to show students that a wave can be paused, not by killing it, but by translating it. There are limits that matter, and they make the story more trustworthy. A memory has a maximum capacity set by how many independent patterns the atoms can keep, without confusion. Noise from stray light or collisions will wash out the phase alignment if you wait too long. Poorly chosen control fields will leave marks that scramble the replay, and no device stores forever, yet each of these costs is known and measured, and engineers can move the knobs to suit the job at hand. Long storage with modest fidelity in a simple glass cell, very high fidelity with shorter storage in a cold trap, or multiplexing many channels in a solid that can be addressed by slightly different colors. If this all seems very far from your day-to-day life, look for the echoes of the idea around you. Your voice traveling through a fiber is already a dance between light and matter, as the glass steers the pulse by its internal resonances. A LiDAR that maps a street waits for faint reflections and aligns them in time to build a shape. A camera sensor stops a single photon, not by catching a bead, but by letting its energy and pattern flip an electron into a state that can be read out. What the newer experiments add is control at the level where the whole pulse can be taken down and stood up again on cue. The human meaning is gentler than the headline suggests. To stop light is not to boss the universe. It is to listen so carefully to a small crowd of atoms that they learn a melody and sing it back. When asked, it is to accept that memory can be a pattern of mutual agreement, rather than a box of stored things. And it is to discover that even something as quick and elusive as a flash can be persuaded to wait without losing itself. So the next time a shaft of sun finds a dusty room, imagine that the room could learn that pulse and set it aside for a while, and then return it to the air unchanged. And consider how much of science is like that room, a set of hands that learn to hold a pattern just long enough to reveal a deeper rule, not by stopping the world, but by teaching it how to pause and remember. Materials that defy friction, the superfluid secret. You expect every liquid to eventually slow and settle, because friction is the quiet tax collector of motion, and then you meet a fluid that refuses to pay, and you watch your certainty wobble as a thin, shimmering film climbs the wall of its container and drips over the rim without a push, as if the fluid had decided that edges are suggestions rather than rules. This is the door into superfluidity, and the first time you peek through it is usually at the point where helium stops acting like a normal liquid and becomes something that flows without internal friction. Picture a pool chilled to a couple of degrees above absolute zero. Nothing dramatic to the eye, just a pale bath under cold light. Yet, if you lower the temperature through a sharp change called the lambda transition, the liquid becomes eerily quiet and impossibly agile. Stir it slowly, and the motion does not fade. Spin it in a smooth ring, and the current can persist for months, because there is no internal rubbing to turn motion into heat. Pull a thin capillary between two flasks. The fluid runs through with almost no resistance. Warm one spot, and the warmth itself pushes flow toward the heat, which is the opposite of your kitchen sink, and has a name that sounds like a magician's trick, the fountain effect. And the film that coats the walls creeps in a sheet, so thin that it can empty a beaker left uncapped, not by cheating gravity, but by allowing the fluid to slip without the usual stick and drag at the boundary. The way to think about this without equations is to imagine that the liquid has split its personality. Most of it behaves in a new collective way that carries no viscosity, and the rest continues to jostle, like an ordinary fluid with some viscosity and some heat. This two-fluid picture is not poetry. It earns its keep by explaining why heat travels in waves through the superfluid, rather than by diffusion. You can ring temperature itself like a bell and watch a pulse of warmth propagate as a tidy wave called second sound. It also explains why stirring gently gets you a silent ghost-like flow, while stirring too hard wakes the ordinary part and spoils the magic with a hiss of dissipation. There is a speed limit hidden in this story. Below a certain critical speed, the flow stays frictionless. Push harder and tiny whirlpools appear that carry away energy and reintroduce resistance. Those whirlpools are not like the ragged eddies in a river. Their circulation is quantized, which is a careful way to say that each vortex spins in discrete packets and cannot spin at an arbitrary slow rate. You can even see the tangle of these threads with tracer particles under very clean conditions. And what you see looks like turbulence written in a new script, a forest of hair-thin lines that reconnect and spring apart, with a rhythm set by quantum rules, rather than by the messy rules that govern a mountain stream. Why should helium become this way at such modest temperatures, while water never does? The short answer is identity, and the long answer is order. The atoms of ordinary helium fall into a class that allows many of them to occupy the same state without elbowing each other aside. Cool them enough, and a large fraction falls into a single shared mode of motion, not a rigid crystal, but a fluid with a phase that stretches across the sample. That order lets the superfluid component glide without the usual friction that comes from random collisions. Push it gently, and there is simply no channel through which to shed its energy into the environment. A second flavor of helium behaves differently. It needs to be cooled 1,000 times colder before it reveals its superfluid face. There, the atoms pair up in a delicate dance, and the dance gives them a collective behavior that again resists scattering. Different microscopic mechanism, same macroscopic miracle, flow that does not tire under the right conditions. This is not a license for perpetual motion, and it is not a loophole in thermodynamics. A superfluid can flow without losing energy to viscosity, but it still obeys energy conservation, and it still gets into trouble if you push it past the threshold where vortices are born. It still exchanges heat with the world, and it still needs careful isolation to keep its quiet virtues intact. The most honest phrase is that it has no internal friction below a critical speed, a phrase that lives happily with every measurement ever made. You can spoil the effect by rough walls that seed vortices or by heat leaks that wake up the normal component. And in thin channels, the smallest impurity can act like a tiny reef that forces the flow to create vortices and shed energy. So the fluid's refusal to pay the friction tax is real, but conditional, and wise experimenters respect those conditions the way a sailor respects wind and tide. The uses of this phenomenon are less flashy than headlines and more durable. The same persistence of flow that keeps a ring of helium moving is the principle behind ultra-sensitive gyroscopes that measure rotation from the tiny shifts in a ring current. The same quantized vortices that dance in liquid helium teach engineers how turbulence might be managed in other settings, because the tangle can be tracked one line at a time. The same second sound that carries heat, like a wave, lets physicists probe tiny temperature differences with a precision that would be impossible in a normal liquid. And the smooth interface of a superfluid with surfaces has inspired designs for bearings that all but eliminate rubbing at low temperature, not to mention the more speculative frontiers, such as the deep interiors of neutron stars, where neutrons are thought to form superfluid phases that shape the subtle irregularities we read as glitches in their lighthouse pulses. A reminder that these quiet lessons in a basement lab scale up to the clocks of dying stars. Even your common sense gains from knowing how this works. Friction in normal fluids is the harvest of chaotic motion at the smallest scales. Every swirl breaks into smaller swirls until the motion dies in heat. A superfluid short circuits that cascade by locking the motion into a phase that cannot easily fall apart. There is no grain in the flow into which you can grind its energy, unless you gash it with enough force to spawn quantized vortices. And those lines do the work that chaos would do in a river, carrying away the excess and heating the normal component. So next time you stir a cup of tea and watch its eddies die, you can imagine the opposite fate in a ring of superfluid where the same motion would circle and never fade. Not because a demon hides in the liquid, but because the fluid is organized so differently that the usual path to rest is not available. The gentle ending to this story is simple. The phrase "no friction" sounds like an invitation to myth, but the reality is richer and kinder. A superfluid is a community of atoms that agrees so thoroughly on how to move that the usual sources of drag have nothing to grip. It climbs walls because a thin film can flow without a cost. It carries heat as a wave because coherence turns random jostling into ordered travel. It spins down only when its orderly pattern breaks into quantized threads. And it fills a quiet corner of physics with a proof that the way matter is organized can change the rules we take for granted. You do not need to memorize the names of excitations or the dates of discoveries to feel the point settle in. Sometimes order is not a crystal, but a river that never forgets its flow, and to learn that such a river can exist at all is to widen your sense of what materials can be and to carry a new question into your day. If friction is not inevitable in a liquid under the right conditions, what other taxes that we imagine as universal might be fees we pay only because we never learned how to live in the gentler regime where nature offers a discount. Crystals that tick forever, without using energy. Imagine a clock that refuses to wind down, not because it steals energy from nowhere, but because it organizes its parts so cleverly that the tick itself becomes a property of the whole and not a job for a spring. And that is the doorway into time crystals, a phase of matter that keeps a rhythm in a world that normally slides toward rest. So begin with a picture that does not lean on metaphors. A crystal in space repeats a pattern of atoms from point to point. A time crystal repeats a pattern of motion from moment to moment. You poke it with a gentle regular tap, and instead of answering on every beat like an ordinary resonator, it answers on every second beat, or every third. The tempo is a clean fraction of the drive, and it stays locked there, even when you nudge the tap or introduce small imperfections. This is not ordinary resonance, where a system rings. When you match its natural note, it is a new kind of order across many interacting parts that share a subharmonic rhythm. The whole acts as one, and it refuses to drift off that shared beat. To understand why this matters, you need two rules that are easy to state. First, equilibrium is dull about time. A system settled into true thermal rest cannot keep a spontaneous motion forever without a feed of energy. Second, interactions often turn gentle taps into heat. If you keep kicking a complicated system, it tends to absorb energy and wash out any tidy motion. Together, those rules once seemed to forbid the very idea of a persistent tick. Then researchers learned how to sidestep both in a lawful way. They moved out of equilibrium on purpose by using a periodic drive whose job is not to pour in network, but to set the cadence. And they arranged the many-body system so that it does not soak up that drive as heat, either by using disorder to localize energy in place, or by driving fast enough that the motion gets stuck in a long prothermal plateau. Within that plateau, the system organizes itself to answer every other beat, or every third, not because it is tuned like a violin, but because interactions enforce a collective flip that takes 2 or more taps to complete. The result is a robust time pattern that can last for many thousands of cycles without drifting. A genuine symmetry breaking in time, but of the discrete kind that a periodic drive allows. The most honest experiments look nothing like perpetual motion machines and everything like careful choreography. In one platform, a ring of trapped ions is addressed by laser pulses that act as the regular tap, while the ions exchange tiny kicks that couple their spins. When the pulses come with a fixed period, the spins settle into a dance that flips only on every second pulse, and the signal in time shows a sharp peak at half the drive frequency that does not walk away as the minutes pass. In another platform, defects in diamond act as a solid-state spin ensemble. A sequence of microwave pulses sets the cadence, and again the spins echo at a subharmonic of the drive, while shrugging off noise that would ruin an ordinary resonance. In superconducting circuits, the same behavior appears in arrays of qubits that can be programmed to bump into one another. The subharmonic peak remains sharp even as small errors are introduced, which is the fingerprint of order rather than fine tuning. And in magnetic materials at room temperature, collective ripples of spin, called magnons, have been coaxed into a state that shows a time crystal like rhythm sustained by a steady pump and dissipation. The tick is not the signature of stolen energy, it is the sign that the system has found a stable pattern of motion that the environment and the drive jointly sustain. The phrase "without using energy" needs care, and the care does not dull the wonder. A time crystal does not draw a net flow of work from the drive while it maintains its tick. It uses the drive as a metronome, and not as a fuel line. In the pre-thermal case, the average energy stops climbing for as long as the plateau lasts and the order persists without heating. In localized cases, the disorder pins energy in place, so the drive cannot smear it into a featureless warm bath. In open dissipative cases, the environment itself plays a role similar to that of a refrigerator, holding the system near a steady state where the rhythm can live. In every case, the accounting is clean, and no law is broken. What is broken is a symmetry. The drive has a period T, and the system chooses a longer one, such as 2T, by committing to repeat, only after several taps. That choice of a longer cycle is as real as the spacing of atoms in a crystal and as measurable. There are limits, and they add credibility rather than take it away. A time crystal is not a clock with perfect eternity. If you make the taps too strong or couple the system too much to uncontrolled surroundings, the motion heats, and the order dissolves. The integrity of the subharmonic peak fades, and the system goes back to being a warm, forgetful crowd. There is also no way to get free work from the tick, because the rhythm does not carry a net energy gradient you can tap. It is a pattern, not a battery, and there are clear tests to separate it from imposters. The frequency of the tick must be locked to a fraction of the drive for a wide range of conditions. It must survive small drifts in the pulses and small defects in the parts, and it must persist for very long times compared with ordinary relaxation. When those boxes are checked, you are not watching a clever resonance. You are seeing time order. Why should anyone care beyond the thrill of a new phase? Because a rhythm that resists disorder is a resource for technology, the way a crystal lattice is a resource for electronics. A network that keeps a stable beat despite noise, can be a building block for timing, sensing, or error-resistant information processing. Arrays of QB that share a subharmonic response can be more robust to certain mistakes. Ensembles of spins that tick in unison can amplify weak signals by locking them to a known cadence, and the steady oscillation itself can serve as a marker to explore the frontier between thermalization and memory in complex matter. In short, it is both a scientific lens and a possible tool. The quiet human lesson is simpler and kinder. We learn early that everything runs down and that anything that keeps moving must be secretly eating. Time crystals teach a subtler thought. Sometimes persistence is not a theft, but a form of order, a collective agreement that reshapes how a system trades energy with its surroundings. And once you see that, the phrase, "tick forever," becomes less like a boast and more like a promise, not of endless power, but of lasting pattern. So when you listen to a steady drip or to the slow flash of a beacon, imagine a material that can hold a beat in the dark, not by burning, but by organizing, and let that idea slow your own mind to a gentler rhythm, where learning is not a sprint, but a repetition that gains strength each time it returns. Shadows that outrun light without breaking physics. You can make a shadow outrun the fastest thing there is, and no law will complain. And the first time you see it, you might feel a small thrill of rule breaking before the explanation quiets the room. So picture a searchlight sweeping across a very distant cliff, or the face of the moon. The bright spot races from crater to crater faster than any rocket could fly, and the dark edge that orders it skims along even quicker. Yet nothing at the cliff is being dragged sidewise by a beam. Each place simply lights up when fresh photons arrive from the lamp, and goes dark when the lamp points elsewhere. The motion you see is a moving pattern, a sequence of separate events with no single object sliding along the rock. And because no particle travels sidewise across the surface, there is no need for a speed limit to apply to that sidewise motion. The only journey any photon makes is from lamp to patch, straight through empty space at the usual limit. Then it is done. Shadows and spots are like the intersection point of scissor blades that can zip along the line faster than any blade tooth. The teeth never move that fast. The location of the crossing does, and locations are not couriers that carry messages. Now slow the idea further and focus on the shadow itself. A shadow is an absence, but its edges are made of a very real change in illumination. When you wave your hand in front of a projector, the distant wall shows a boundary that races across as you move. If the wall is far enough and your swing wide enough, that boundary can outpace light, and still you have broken nothing, because the instruction that tells the boundary how to move is not sent along the wall. It is sent through space from your hand to each point independently. Each patch of the wall learns about the motion only when the light that would have reached it is blocked or unblocked. And that news can never arrive earlier than light would have arrived, had nothing been there. In other words, the earliest flicker, the first appearance of the dark, obeys the fundamental limit. Only once the pattern is established can the apparent edge outrun it as a line of changing places that share no sideways cause. This difference between pattern speed and signal speed is the whole trick. It shows up in waves as well. The crests of a rippling field can march with a phase velocity that is faster than the limit in certain media and at certain colors. But the envelope of a pulse that carries information obeys a stricter rule, and the very first rise of a pulse, the front that announces new content, is constrained by the speed at which the medium lets causes propagate. In the clearest case, that limit is the constant of the vacuum. The stories you may have heard about light pulses that seem to leave a medium before they enter are all tales of reshaping. The front does not jump the queue. The middle of the pulse is distorted by the material, so that the peak slides, and the data hidden in the rising edge never beats the limit. Clever optics can make a hump run ahead. Causality keeps the first hint honest. Out in the world, shadows and their racing borders show up in places so ordinary that your eyes stopped noticing long ago. The line between daylight and nighttime runs across our planet at speeds that can be faster than a jet and slower than a sloth, depending on latitude and season. It is a racing boundary without a body. On the rings of Saturn and the belts of Jupiter, the shadow of a transiting moon can whip across clouds, faster than a spacecraft could ever chase it. The night that falls on a mountain as the Sunday drops can sprint across distant snowfields at superluminal pace, while every grain on every ridge is only learning, one by one, that the Sunday has gone behind a peak. In a stadium, a rotating spotlight draws an oval on low clouds, and the bright dot can cross miles quicker than the escape velocity of any vehicle. And still you learn nothing faster than the lamp can tell the clouds. The spot is a line of events stitched by your eyes. Engineers use the same principle with a smile. A scanning laser writes images by jumping the aim between pixels. The bright dot looks like it moves, but the machine is putting separate packets of light on separate spots. Nothing is flowing along the glass faster than light. A LiDAR sweeps a street with a beam and computes distances from the time of flight of photons. You could spin the beam so rapidly that the apparent arc on a far wall would outpace any particle, and still the only information that matters is the set of delays between launch and return, each one bounded by the same speed. This is why you cannot turn a superluminal shadow into a message that beats a radio signal. To make the shadow tell a story to a faraway friend, you would have to waggle the blocker here, and the news of each wiggle would still have to travel through space in the light that is either blocked or unblocked. Your friend could not read the next chapter before you wrote it. The same caution helps you sort other optical mirages. Astronomers sometimes report features in glowing jets that seem to crawl across the sky faster than light. That appearance is born of geometry and timing, rather than a true courier that outruns photons. A bright knot moving almost toward us can change its angle while its light is still reaching us. So later, flashes arrive closer together than you would expect, and the knot seems to skate across the sky with impossible speed, even though every particle in it stays within the local rules. The way to keep your balance is to ask a plain question. Is there a single object or bit of information that must pass from A to B along the line where the fast thing seems to move? If the answer is no, if the fast thing is a place where other lines meet, a crossing or a boundary or a phase of a wave, then you are in the safe country of pattern speed. There is an even subtler version of the lesson that hides in photographs of laser beams crossing smoke. A bright X seems to slide along the beams where they meet, and you can make that crossing dance faster than any car by rotating a mirror. But the photons in either path only run forward into the smoke. No one is recruited to sprint along the crossing, and the brightness that appears to move is the result of fresh photons arriving and scattering to your eye. From each new location, it is a parade of locals waving, not a courier racing with a baton. All of these examples do more than rescue a speed limit. They show you how to think like a physicist when the world tempts you with a paradox. Look for what is actually traveling. Look for what carries energy or a new bit of information. Follow that thread and you will find that the limit lives in the right place. In the real passage from cause to effect, not in the cartoon line that your eyes draw between separate events. And the human lesson is as calm as the science. Many things in life look like urgent motion, but the only motions that truly change a story are the ones that carry meaning from one heart to another. A shadow can sprint, but it cannot speak faster than its source. A rumor can spread, but it cannot outrun the truth that seeds it. So the next time you see a flashlight sweep across clouds or a mountain fall into night, in a single blue breath, let the beauty stand and let the laws rest easy. Nothing illicit happened, only the choreography of separate touches that your mind gathered into a running shape. A reminder that the universe is precise enough to keep its promises even when it looks as if a ghost has passed you in the dark. Voids that glow when you move. The Unruh effect, what would it mean if empty space could warm as you press the gas and cool as you ease off? Not because a heater hides in the vacuum, but because the very act of accelerating changes what counts as nothing. So let us begin quietly with a single idea that you can hold in your hands. A thermometer can only read what its own motion allows it to read. And if you keep it drifting steadily, it reports the deep cold of empty space. Yet if you strap that same thermometer to a rocket and give it a constant push, the dial begins to creep upward, as if a faint thermal fog had appeared around it. This is the Unruh effect, and its claim is simple enough to state: an observer who accelerates through the vacuum finds that the vacuum looks like a warm bath. The temperature does not depend on speed. but on how hard you press. Stronger acceleration means a higher reading, and there is no mystery energy being created, because the heat you measure comes from the work you are doing to stay accelerated. The engine that pushes you pays the bill. To see why this is not a word game, imagine a very small detector that can sit in a quiet lower state or jump to a higher one when it absorbs a packet of the field. In steady flight, it rarely clicks because the vacuum is as empty as it can be. But under steady acceleration, the same detector begins to click at a rate that matches what a warm gas would do. In that sense, the detector is not hallucinating. It is exchanging real energy with the field because your thrust shakes its coupling in a way that mimics thermal noise. There is a geometric reason behind this change, and it is gentler than the formulas that first revealed it. A constantly accelerated observer is forever cut off from part of space by a line that no signal from behind can cross. A personal horizon forms just as surely as the wake behind a ship forms, and the presence of that horizon reorganizes how the field modes add up. The bookkeeping of what counts as a particle and what counts as empty is different. Once a horizon splits the stage, to you, the horizon glows. To a drifting observer with no horizon, there is no glow. The two stories are not contradictions, because they are about two different motions and two different sets of accessible events. Numbers turn this from poetry into discipline. The temperature rises in direct proportion to acceleration, and the scale is so severe that an everyday push gives a reading that is unbelievably small. Even the strongest laboratory centrifuges, or the most violent roller coasters, would not budge the dial by any amount you could measure. To feel a single Kelvin, you would need an acceleration so fierce that no human body and no ordinary machine could survive, which is why the effect has not been cleanly seen in the sky or on the lab bench, despite being one of the most solid predictions of quantum field theory in curved or accelerated settings. Still, there are clever paths forward. Electrons whipped by ultra-intense lasers experience enormous accelerations, and their radiation may carry tiny fingerprints of the effect in the fine structure of the spectrum. Trapped ions and superconducting circuits can be driven in ways that simulate acceleration and allow a small artificial atom to click as if it were moving through a warm vacuum. Acoustic and optical analogues that create effective horizons also echo the same logic, not as final proof, but as steady hints that the mathematics is not playing tricks. If the vacuum can be warm for you and cold for me, does that break the second law, or allow sneaky machines that squeeze work from nothing? It does not, because all the accounting includes the agent that keeps you accelerating. The energy you could draw from the apparent bath is precisely the energy you feed to the engine. Try to use the effect to run a heat engine, and the best you can do is move energy from your fuel into useful work by way of the thermal clicks your detector experiences. The bath is not a universal resource that an idle observer can tap. It lives in the relation between your motion and the field. The effect also stitches together ideas that might otherwise seem separate. Near the surface of a very dense object, where you would have to fire rockets hard just to hover the Unruh temperature for your acceleration, is close in spirit to the temperature that a stationary observer attributes to the horizon of that object. The link is not an identity, but a kinship. Both teach that horizons and motion change the way vacuum looks, and both say that radiation can be the most conservative of consequences when fields are placed in extreme conditions. Yet, even if you never stand near a compact star, the quiet lesson remains. Particle content is not an absolute label pinned to the world. It is a relationship between a state and a measurement made along a path. Change the path, and you can change what it means to count quanta. There are subtleties worth keeping in the open, because they guard the core idea from misuse. The temperature here is not something you can feel with your cheek pressed against a window as the rocket fires. It is a response rate for appropriately designed detectors, and not every detector is appropriate. One must be able to couple to the field in a way that allows the clicks to be counted without swamping them with ordinary noise. There is also the fact that an accelerated charge radiates in any case, a classical statement that is not the same as the Unruh story, but must be reconciled with it. The correct reconciliation is that different observers divide the total energy exchange into different parts. One calls it radiated, another calls it absorbed from a bath. The sum is agreed, but the pieces depend on the frame. Again, no law is bent because all observers who compare their full ledgers come to the same total. You may wonder whether this glow could matter for technology beyond its role as a teachable example. Perhaps not in the way a battery matters, but possibly as a limit in devices that chase ultimate precision. A quantum sensor that is accelerated, or a quantum link stretched around a fast maneuver, may experience a noise floor that has the flavor of Unruh. And network designers who dream about moving quantum states between satellites and fast craft keep this possibility in mind. Not because it dominates the error budget today, but because it testifies to a principle that only grows more relevant as we push deeper into regimes where motion and quantum information meet. Bring it back to the human scale, and what remains is a clear way to think about emptiness and effort. The world does not hand out an objective catalogue of particles independent of how you travel. Emptiness is not a single silence, but a family of silences. And when you accelerate, you choose a member of that family, in which there is a soft murmur that was not there before. The murmur is not a fantasy, and it is not a free lunch. It is the honest echo of your own push written into the field that fills space. So, if you want a picture to carry with you, think of the vacuum as a lake, so still that a floating leaf barely turns. Set yourself rowing and you will feel a breeze that was not there for the leaf. Not because the lake had a wind all along, but because motion and medium together decide what counts as calm, and then end gently with this thought, that the universe is more relational than our first lessons suggested. Even nothing can acquire a temperature when you insist on a certain kind of journey, which is another way of saying that how you move through the world helps decide what the world looks like to you. A fact both humbling and oddly comforting in its quiet consistency. Plates that pull each other closer. The Casimir mystery. Place two silent, uncharged, mirror-smooth plates face to face in a vacuum. Turn off the lights, walk away, and the patient surprise is that they begin to creep together, even though you added no battery, and no magnet, and no glue. As if the nothing between them had learned to push. The clean explanation starts not with mystery, but with a simple picture of waves in a box. Any cavity can host only certain patterns of vibration, much as a guitar string accepts only notes that fit cleanly between its ends. And when you slide two plates close together, you create a thin cavity that refuses to host most of the restless ripples that normally flit through empty space. Outside the plates, there is room for more patterns. Inside, there is room for fewer, and the imbalance shows up as a tiny pressure difference that nudges the plates inward, a force that is not electricity and not magnetism and not ordinary air pressure, but a quiet bookkeeping effect of how boundaries edit the allowed ways fields can wiggle. You need no equations to follow the logic. Think of a library where some shelves are removed. There are fewer places to file books inside than outside. If the filing system tries to even things out, it pushes on the walls. And in physics, that filing system is the zero-point activity of the electromagnetic field, the baseline jitter that remains even at very low temperature. Not as a source of free power, but as a background that boundaries can reshape. The force is strongest when the gap is tiny, and it fades rapidly as you pull the plates apart, which is why it eluded our senses, until experiments learned to tame and measure separations smaller than a grain of smoke. The careful part is proving that the pull is real, and not a trick of stray charges or dust. Modern measurements often compare a curved surface to a flat one, because it is almost impossible to hold two plates perfectly parallel at nanometer distances. A tiny torsion balance or a micro cantilever feels the attraction as a delicate twist or a shift in resonance. Teams polish surfaces until they shine, scrub them of static, and still must correct for small patches of voltage that cling to metals the way freckles cling to skin. They also account for surface roughness and for the fact that real plates are not perfect mirrors at every color of light. The full theory that connects materials to forces we read in the lab is called a finite conductivity treatment inside a broad framework for media. It blends the optical response of the plates with temperature and geometry, and it shows that the tidy parallel plate picture is only the beginning of a family of related effects that includes sphere to plate, corrugated to flat, and even plate to plate with a liquid in between. That last case carries a delightful twist. If you choose two different materials and slip a carefully chosen fluid between them, the ordering of how each medium reflects field fluctuations can flip the sign of the pressure so that the plates gently repel rather than attract, not as a violation of the rule, but as another verse of the same song. The boundaries have been arranged to allow more wiggle room in the gap than outside, so the pressure difference pushes outward. There are other variants as well. A small torque is predicted and has been seen between plates that prefer vibrations in one direction over another. The plates try to rotate until their preferred directions align, which reads like a compass built from light that has not even been launched. What of energy? There is no treasure buried in the vacuum. When the plates move together, they do work on your sensor, and that work comes from a reduction in the stored energy of the field configuration. If you then pry the plates apart, you must pay that work back. Sometimes quickly, sometimes as slow labor against a gentle pull. The balance sheet closes to the last joule and claims that this force can be harvested as an endless power source, always fail at the first careful audit. Because a battery needs a persistent difference, and the ground state has none until you create one by changing boundaries. The energy you get out is the energy you put in, shaped by the geometry you built. The Casimir pull is not only a curiosity, it matters in technology at the scale, where moving parts are small enough that surface forces outweigh weight. Tiny machines in silicon can seize when parts come too close, and the same force that delights a physicist becomes a nuisance that engineers must dodge with textured surfaces, coatings, or designed motion that avoids prolonged intimacy. The flip side is that the pull can be used as a gentle actuator or as a standard to calibrate sensors that weigh forces far smaller than the tug of a single grain of sand. Researchers also play a deeper game in which boundaries are changed quickly, rather than slowly when you change the conditions faster than the field can keep up. Pairs of real photons can be emitted from what began as silence, a dynamic version of the effect that has been coaxed to life in superconducting circuits, where a mirror-like boundary can be moved in effect by rapidly modulating an electrical length. The photons come with the right statistics and colors to show that you shook energy out of your driving source into light by changing the stage on which the field must perform. The story is richer still when temperature joins in. At room temperature, there is a low thrum of thermal photons everywhere, and when the gap is large enough that only long wavelengths matter, those thermal ripples tilt the balance in a way that precise experiments can see. Measurements across distance ranges from tens of nanometers to micrometers knit together a tapestry that matches the full theory only when you feed it the correct optical properties of the actual materials. A quiet victory for the idea that empty space is not a featureless void but a stage whose rules depend on the scenery you build. Professional caution has made the field sharper rather than softer. Early measurements sparked debates about how best to treat the optical response of metals at very low frequency, and about how to model the small electrostatic patches that seem to live on even the cleanest surfaces. Those debates pushed both measurement and theory forward until the two locked together over broad ranges, which is what you hope to see when nature is being read correctly. A convergence that leaves only small differences to be explored or to be used as windows into new physics, if any should appear. What does this mean for the way you think? It tells you that closeness can create a force not by contact but by context, that two objects can feel a pull because the space between them allows fewer possibilities than the space outside. It says that silence has a structure, and that the structure can be shaped by how you arrange the world. It suggests a gentler attention to boundaries in your own life, because boundaries do not just separate, they also select. They decide which patterns can live and which must fade. And sometimes the right arrangement brings a quiet attraction that would never have appeared in an open field. So the next time you see light glint between two panes of glass or a hairline gap in a machine, consider that there is a soft conversation going on in that sliver of space, a pressure written by permitted and forbidden ripples, and let that thought slow you for a moment. Because the universe is telling a story there in a whisper, a story in which nothing pushes something, and yet nothing lies. Only the measure of possibilities changes with distance, and the result is a touch you can weigh. Particles that borrow energy and pay it back instantly. Imagine a world where the rules are strict, yet the appearances are slippery, where an interaction can seem to borrow a little energy and then settle the account before anyone can complain. And you are invited to watch closely enough to see how the trick works without breaking a single law. Begin with a clean picture of a collision at microscopic scales, say two electrons approaching and veering away. Your detector registers no light emitted between them, and yet they exchange momentum as if a messenger ran briefly from one to the other. In the language physicists use, that messenger is a virtual photon, and the word virtual means it is not a free particle that your camera could ever catch. It is a temporary pattern in the electromagnetic field that links the start and the end of the event, a ripple that does not meet the relation between energy and momentum that real photons must satisfy. It lives only inside the calculation and inside the very short interval during which the interaction unfolds, and when the books are balanced at the end, energy and momentum are exactly conserved in the ordinary way that your intuition demands. The headline phrase about borrowing comes from a careful but subtle idea. When a process is confined to a very short time, you cannot define its energy with perfect sharpness. Not because anyone is careless, but because the rules of the quantum world say that precision in time and precision in energy trade with each other. For durations that are tiny, the allowed blur in energy can be larger, and that blur is what lets the internal messenger carry values that would be forbidden to a real particle. The larger the mismatch, the shorter the time during which such a contribution matters. So the amplitude for that process falls away rapidly as you demand a bigger violation. This is why the picture of alone is useful, and also why it misleads. If you push it too far, nothing material leaps out of nowhere. There is only a temporary bookkeeping flexibility that vanishes the instant you ask for an observable outcome. At the end, you will find no extra coins in the universe, and no deficit either. Only a different sharing of momentum and energy between the real particles that went in and the real particles that came out. Once you accept that virtual quanta are internal links, rather than independent actors, a whole set of forces becomes less mysterious. The strong pull that binds a proton can be viewed as quarks exchanging virtual gluons, and even virtual pairs of quarks and antiquarks inside a very rounded and energetic field. The short reach of the weak interaction can be traced to the fact that its messenger is heavy, and thus any off-shell excursion dies almost immediately in time, which is why processes like beta decay happen, but only within the tiny range set by that lifetime. In the older nuclear picture, the bite that holds nucleons together can be modeled as the trade of virtual pions, and the limited lifetime of those exchanges sets the finite range of the nuclear force. You can carry the same logic into precision tests at accelerators, where the chance of producing a given final state is shifted by loops of virtual particles that momentarily circulate inside the field. Heavy quanta that cannot be produced directly at that energy still leave fingerprints by changing the probabilities. And this is how very accurate measurements of scattering have revealed the way the electromagnetic coupling weakens at long distance and grows at short distance. A running that arises because virtual pairs in the vacuum screen charge the way a crowd can hide a speaker from view. You might worry that if virtual particles can pop in and out, you could mine them for power. But the universe never lets you set up a pump that runs on a blur. What instruments register are real quanta that satisfy the strict relation between energy and momentum. And those only appear when an interaction leaves a durable record inside the diagrams that help us compute. There are many imagined routes from start to finish. Some of those routes include internal quanta that are very far from the values a free particle could carry. And yet, you cannot pause the story midstream and snatch one out. Try to box it, and you are no longer describing the same process, and the probability you compute will change to reflect the new rules you imposed. The lone metaphor is only safe so long as you remember that there is no bank, only a calculation that weighs many possible histories, and then delivers a single outcome that respects every conservation law. The idea pays off most clearly in cases where the messenger could never be real at the available energy, and still the event proceeds. Inside a neutron, a down quark turns into an up quark by emitting a virtual W boson that almost instantly becomes an electron and an antineutrino. The W is so heavy that there is no chance of creating it as a free particle in an ordinary decay. Its presence is a brief internal handshake, and the feebleness of the process follows from how far off shell that messenger must roam. At higher energies where the W can be made as a real particle, the same theory predicts a surge in events, and that surge is exactly what colliders have seen. A tidy example of how the virtual story and the real story are two faces of one rule. There is also a profound but testable way in which virtual clouds reshape what seems like a property carved in stone. The magnetic moment of the electron is not exactly the simple value that early theory would give. It is shifted by a small amount that countless experiments have measured, and that countless calculations reproduce, by adding the effect of many possible loops of virtual quanta. A charged particle is never alone. It sits inside a swarm of ephemeral excitations, which alter its field by a traceable amount. The agreement between theory and measurement here is among the best in all of science, and it is hard to imagine a better confirmation that virtual contributions are not just a story we tell ourselves, but a necessity if we want numbers that describe the world. At this point, it is fair to ask what a virtual particle really is, and the kindest answer is that it is not a thing. It is a term in a sum, a way of organizing a calculation so that cause and effect are local, and the timing of events is respected. Different ways of doing the mathematics can reshuffle which terms are called particles, and which are called background. And yet the final predictions for physical outcomes agree that should cool your appetite for literal pictures without making you cynical. The images of short-lived messengers are crutches that help the mind, while you learn to trust the algebra that never lies. The human lesson is gentler than the headline. The world is honest to a fault, and never hands out free energy. And yet when you look at the smallest scales, you must learn to think in amplitudes rather than certainties. You must accept that many near stories contribute to the single true story you will finally observe, and that during the blink in which possibilities mingle, it is sensible to speak of a brief loan that is always repaid. The prize for that discipline is clarity, a better sense of which metaphors guide and which mislead, and the calm realization that nature does not cheat when it seems to. It only uses a deeper accounting system than the one we first learned, one in which borrowed means weighted, and repaid means that the final state matches every rule we can check. Forces that push the universe apart, and we don't know why. You grew up with a rule, so plain it fit in your pocket. Gravity pulls, and the pull should slow the expansion of space. And then you learned that the opposite is happening. The distances between faraway galaxies are growing faster with time. And the honest phrase for the agent behind this is that we do not know. So let us start with what we do know, and why we are sure of it. We map the sky in several independent ways, and each one says the same thing with a different accent. Ancient ripples frozen in the afterglow give us a yardstick for size. The pattern of galaxies today preserves a faint echo of those ripples, and that echo tells us how the scale of the map has changed. Light from certain exploding stars arrives with a characteristic brightness that lets us judge distance. And when we compare distance with the red tint that marks stretch, we read not a steady pace, but an accelerating one. The conclusion is not fragile, because the methods disagree in their errors, and still agree in their story. Now comes the puzzle. What can push without being a wind? The most economical answer is that empty space itself has a uniform energy whose pressure acts like tension and drives expansion to speed up. The next answer is that there is a new field spread across the cosmos that changes slowly and mimics a constant today, but might drift tomorrow. A third cluster of ideas says that our law of gravity lengthens its reach or changes its grip on the largest scales, so that the same energy and matter do a different job than we expect. And around these possibilities sits a fence made of measurements that grows taller every year. To tell these stories apart, you cannot look only at the size of the universe. You must watch how structures grow. When gravity wins, small ripples in matter swell into galaxies and clusters at a rate that follows from the same rules that set the expansion. A true new energy that is smooth should slow growth by making space accelerate while leaving the law of gravity itself unchanged. A change in gravity should often alter growth directly and change how space bends light compared with how it pulls on matter. So we weigh galaxies with weak lensing and listen for the drift in the velocities of galaxies, caught by their neighbors, and count the rare giants that form from the deepest wells. We ask whether the bending of light and the tug on matter match the same script. We test the rule that ties density to potential in regions of different size and different age. And while the present record mostly points to a smooth background energy doing the pushing, small mismatches keep the conversation alive. The expansion seen in early light and the expansion inferred from nearby ladders do not quite agree. The growth of clumps looks a shade slower in some surveys than a simple model would like. And these tensions could be a call for better calibration, or a hint that we are missing a part of the play. Modified gravity ideas face their own gauntlet, and the sky has already closed some doors. A shock of light and gravity from colliding dead stars arrived almost together, which tells us that ripples of space-time travel at nearly the same speed as light. That single fact rules out broad families of theories in which gravity waves lag or lead. Other proposals must hide their extra pull in crowded regions through screening tricks that weaken any fifth force in dense environments, while letting it act in cosmic emptiness. Such models can be tested by comparing how dwarf galaxies fall in clusters with how their light is lensed, by watching how stars move in the outskirts of galaxies, and even by hunting for tiny shifts in laboratory experiments that bring test masses close without letting them touch. So far, the best designs leave little room for a large change, yet still allow narrow avenues where gravity could be different at just the right scales to ease our tensions. The field view for a new energy component brings its own challenges. A gently rolling field can explain acceleration, but must be remarkably light and feeble to avoid disturbing the tightly measured physics of the early universe. And the formation of the elements, it must be calm enough not to create lumps that would add structure where none is seen. And it must explain a coincidence that nags at the mind, why the push of this field becomes important just when galaxies like ours have formed. There are clever variations that put some of that push earlier in cosmic history, or that tie it to interactions with matter in a way that turns on only recently. Each version makes testable promises about how distances scale at intermediate look-back times, and about the detailed pattern of clumping, and new surveys are built to catch them in a lie, if they dare tell one. The most radical answer would be that we have misread the bookkeeping of averages in a lumpy universe, and that the global acceleration is an illusion born of adding up many local slowdowns in a curved geometry. Patient work has shown that this path is steep. The effect of lumpiness on the average expansion can be computed and appears too small to account for what we see. But it remains a useful discipline, because it forces us to keep track of exactly what is being measured when different telescopes look at different tracers. What is next feels like an engineer's dream. A direct watch for the drift of redshifts over decades that would reveal the changing pace without any model in between. The use of gravitational waves from merging stars as standard sirens that carry their own distance scale, without calibrations from ladders, the steady sharpening of weak lensing map, as in galaxy motions across half the sky, and the tie between these late-time probes and the subtle polarization patterns in ancient light that record how matter stood at the moment when the fog first cleared. Each new thread tightens the weave and leaves less room for stories that only work when data are thin. Through all of this, it helps to keep two thoughts at the front of your mind. First, that the phrase "we do not know" is not an admission of failure, but a promise that the question is good. And second, that not knowing why the universe accelerates does not mean that anything goes. Conservation of energy still holds, in the only sense it can hold in an expanding space-time. Cause and effect still order events. The speed limit still binds. What we are missing is the deep reason for a gentle negative pressure or for a softened pull at scale. And until we have that reason, we split our effort between making cleaner maps of distance and growth and trying out new symmetries that could explain a push we did not expect. There is a quiet human meaning in the way this mystery sits. The largest driver of the future seems to be something that does not clump or glow, and yet steers the fate of all that does. A reminder that absence can shape as much as presence. And there is a practical meaning too. The instruments built to answer this one question are already improving weather models by mapping the air with exquisite, E-detail, unmasking small planets around distant suns through stable optics and training a generation to read noise without being ruled by it. So when you hear that a force pushes the universe apart, and we do not know why, translate it into a gentler truth. We have a reliable description of what the cosmos is doing, and several good ideas for why, most of them already leaning against the wall of data. And the work now is to keep asking the sky the kind of question that leaves only one answer, standing when the music stops. Matter that shouldn't exist, and its antimatter twin. You wake into a universe that looks full of ordinary stuff, and only later learn that by all rights it should have destroyed itself in a bright zero. Because for every particle, the same laws allow a mirror partner with opposite charge, and when matter meets that partner, they vanish in a quick flash of light. So the first puzzle is not how antimatter is made, but why any matter was left over it all. And the cleanest way to feel the puzzle is to imagine the first seconds after the hot beginning, when pairs of particles and antiparticles were born in nearly equal numbers, and then met again as the cosmos cooled. If equality had been perfect, the last glow would have faded into a sea of photons, with nothing solid to come later. No stars, no chemistry, no you. Yet our telescopes see galaxies and our labs see protons and electrons, which means nature tipped the balance by a hair. About one matter particle for every 10 billion pairs gained a tiny advantage and survived the mutual burning away. We read that left over in the faint afterglow that fills the sky, and in the counts of ordinary atoms today. So the question becomes, who tilted the scale, and by what lawful trick? The ideas that have stood the test of time are spare and demanding. To build a universe with a small excess of matter, you need 3 ingredients to work together. There must be processes that can change the total tally of matter, like reactions in the very early plasma that juggle quarks and leptons. There must be a difference in the way the laws treat matter and antimatter, called CP violation, so that forward and backward routes do not cancel perfectly, and the whole show must run out of step with perfect thermal balance, so that the universe cannot simply reverse the bookkeeping and erase the excess. With those conditions, you can sketch many paths. Perhaps the Electroweak force once allowed rare events that do not respect the simple count of baryons, and that a small built-in preference for one sign over the other pushed the net upward, while the cosmos expanded out of equilibrium. Perhaps neutrinos, which are the shyest of known particles, carried the first asymmetry, and later handed it to quarks through reactions that connect the two sectors. This is called leptogenesis, and it depends on neutrinos having a special identity that we do not yet know they possess. There are still more speculative routes that call on new fields that rolled and decayed, or on hidden forces that showed up only in the first instance and then faded. The point is that the ingredients are simple to say, yet the recipe is still being tested. What makes this a scientific problem and not a fireside story is that we can test pieces of it in the lab. We have seen CP violation in the decays of kaons and B mesons, and more recently in cousins that carry charm. The pattern we have measured so far is real, but too small by many orders of magnitude to account for the cosmic excess on its own, which tells us that the full answer must include new sources beyond the familiar quark mixing of textbooks. We search for those sources by looking for an electric dipole in the neutron or the electron, which would be a tiny internal arrow that flips under time reversal. The best experiments have chased this arrow to astounding precision and keep finding nothing. A non-result that is itself a powerful guide, because it closes whole regions of theory space and forces ideas to sharpen. In parallel, giant underground detectors listen for a rare nuclear decay that would reveal that neutrinos are their own antiparticles, which would open a clean path for leptogenesis. We have not seen that decay yet, and the machines grow more sensitive each year. And at colliders, we look for new heavy states that could have mediated the early imbalance, but that now would show up as unexpected bumps in the distribution of events. Those bumps have not appeared either, which again is a result that reshapes our search. Antimatter is not only a thought experiment. We make it, we catch it, and we put it to work. Positrons were first traced in the arcs of a cloud chamber in the last century, and today they light up medical scanners in hospitals, where a short-lived tracer emits a positron that meets an electron and the twin flashes. that follow are recorded to build an image of living tissue. Antiprotons are created in accelerators by slamming energetic beams into targets, and then collected and cooled, and whole antiatoms have been assembled and held in magnetic bottles for long enough to probe their properties. Teams have compared the color lines of antihydrogen with those of ordinary hydrogen, and so far they match to an impressive number of digits as the principle of CPT symmetry demands. Researchers have even watched how antihydrogen falls under Earth gravity, and the first results say that it falls down as any sensible thing should within generous uncertainties. None of this solves the cosmic imbalance, but each piece deepens our confidence that the rules are consistent. Matter and antimatter follow the same grammar where we can check, and the missing tilt must appear in places we have not scanned or at energies we have not reached. On the larger scales, the sky is quiet, where a violent boundary would shout if an entire galaxy of antimatter drifted near a normal one. The boundary between them would shine in gamma rays from endless annihilations. We do not see such scars, which suggests that our local patch is made of matter end to end. Balloon and space-based detectors have chased the rarer possibility that heavy antimatter nuclei might float in from far away, and a few events have been debated, but none has yet convinced the community that an anti-galaxy haunts the near universe. The most conservative reading is that any antimatter islands must be impossibly far or else entirely absent, and that most of the cosmos shares our chirality of charge. Against this backdrop, the human mind still wants a story with a single switch we can point to. But the data teach patience. Nature often wins with a combination of small biases, applied early and amplified by circumstance. When you read that the universe should not exist, what you are really hearing is that our first simple symmetry arguments predict a draw, and that every confirmed deviation from symmetry so far is too mild to choose the winner on its own, which is not despair but invitation. It tells you exactly where to push. Measure the patterns of CP violation with absurd precision. Keep hunting for dipoles. Test the gravity and the spectra of antiatoms. Rebuild the ladders of cosmic expansion and structure growth to cross-check that the counts of photons and baryons in the afterglow are as we think they are, and refine neutrino machines until they can decide whether these ghostly particles carry the missing key. There is a gentler meaning tucked inside the physics. The fact that almost everything you see is the residue of a tiny imbalance makes the world feel precarious at first, and then precious. A universe that could have been empty found a way to keep a grain of matter for every many grains of light, and from that grain arose stars and carbon and hands that could write this sentence, not because the cosmos cheated its own books, but because the books allow a lawful bias if the conditions are right. So when you hear that matter should not exist, and yet does, translate it into a calmer truth. Symmetry is a guide and not a prison. Small asymmetries written early can shape everything that follows, and the work of science is to trace those first strokes until the outline of the story appears. Not to make the world less wondrous, but to show how wonder and law can live in the same room. Dimensions that might hide gravity beyond what we see. Suppose the room you live in has more doors than you can see, and the reason you never noticed is that most of them are sealed so tightly that only gravity can slip through. Not because it is special in a mystical way, but because it is the one field that does not mind spreading into every corridor the universe allows. And that is the starting point for thinking about extra dimensions, not as science fiction, but as precise proposals that try to explain why gravity is so weak, compared with the other forces, and why its pull thins out so quickly with distance. The first step is gentle history. A century ago, a mathematician asked what would happen if space had one small extra direction rolled up like a hidden circular hallway, and found that when you write the equations of gravity, in that slightly larger room, a familiar force appears in disguise. Something that looks like electricity in the three visible directions. A hint that geometry can carry fields. The way a violin carries harmonics, later generations turned that hint into a broader program, where all known particles are ripples on shapes that may be tiny and curled. The important part for you is the picture it suggests for gravity today. If space has more directions than we see, and the other forces are pinned to a kind of sheet where matter lives, gravity alone would be free to wander into the full space, and its field lines would spread out into those unseen directions. The dilution would make it look weak on our sheet, even if it is not weak in the larger whole, like a voice that sounds faint in a crowded cathedral, not because the singer is timid, but because the sound is filling every aisle at once. This idea is not a license to dream anything you want. It comes with sharp tests. If there are extra dimensions that are large, compared with an atom, then the familiar rule that gravity falls off with the square of distance would change over very short ranges, because the field would have extra room to fan out. So experimenters built tiny balances with torsion fibers thinner than hair and brought small test masses almost into touching distance while cants, stray electric forces and the gentle pressure we spoke about in other contexts. The result is a map of the force at submillimeter scales that so far matches the old rule to exquisite precision, and tells us that if extra directions are broad, they must still be smaller than those distances, or else their influence would already have been seen. That is a clean kind of no that sharpens the search rather than ending it, and it is complemented by a second test at the opposite extreme. If space is larger than it looks in ways that matter to high-energy collisions, then smashing particles together should sometimes launch a graviton into the hidden directions. To us, the event would look like a spray of debris recoiling against something that does not return to the detector, a missing energy signature with a distinct shape. Colliders have collected mountains of such events, and the pattern so far fits the expectations of known backgrounds, which again does not kill the idea, but draws a fence around its parameters. The extra corridors must be smaller or more warped than certain optimistic versions suggested. Warping introduces a second family of models that are as tidy as they are surprising. Instead of adding broad flat rooms, you bend the additional direction so that distances and energies are redrawn as you move along it. In such a space, most of the extra volume is effectively out of reach for our particles while gravity can still feel it. The bending concentrates gravity near one region and makes it look weak on our region, like a stretched sheet that funnels marbles toward a seam. This warped picture would show itself through heavy echoes of the graviton, additional resonances that share its identity, but sit at higher masses like notes in a harmonic ladder. Teams have hunted those notes in the distributions of 2 photon and 2 lepton events, with meticulous attention to detail, and have found none so far, which again trims the freedom of the theory and helps decide which shapes are still plausible. You can ask what extra dimensions would do outside the lab, and the answers are as practical as they are romantic. If gravity can leak into a bulk beyond our visible sheet, then the way structures grow across the universe might change in subtle ways. Light that bends around heavy clusters of galaxies could see a slightly different relation between mass and curvature than the one we infer from the orbits of galaxies. So we measure both with growing precision and compare them to see if a hidden hand is at work. The same logic extends to the faint ripples of space-time we call gravitational waves. If the waves can diffuse into extra corridors as they travel over large distances, then a faraway merger might look dimmer than expected for its measured distance, while the light from the same event would not be dimmed in the same way. The first catalogues of such events have not demanded this leakage, but future measurements will push the comparison into regimes where even a small leak would stand out unmistakably. The key is that each probe asks a different question, and agreements between them make it hard for a mistaken idea to hide. The concept of extra dimensions also rearranges how we think about mass and charge at a deeper level. In the language of fields, a small circular direction gives rise to a tower of excitations with gradually increasing energy, faint steps that would correspond to heavier partners of known particles. These are called modes of the hidden direction, and they too can be SOC, as bumps in collision data, or as small alterations in the behavior of forces at high energy. They have not been found which forces the radius of the circle to be very small or the warping to be very strong. But the search is young by the standards of cosmic history, and the techniques that were built to test these pictures have already given us more accurate knowledge of many other parts of nature. A good sign that even a negative result can be a gift when the question is sharp. There is another path to extra dimensions that grows from the mathematics of strings, which suggests that particles are not points, but loops that vibrate, and that consistency of their vibrations requires more directions than we see. In that program, the shape of the small hidden space is not a detail, but the source of the types of particles and their interactions. A different shape gives a different low-energy world. And while this framework is not an experiment by itself, it provides a dictionary that links geometry to physics and inspires precise calculations that can be tested wherever they touch observation. It also teaches a human lesson about humility. The way the world looks at our scale may be a projection of a deeper structure that only reveals itself indirectly, like a shadow that hints at the form of a hand just outside the window. A fair concern is whether these ideas are simply moving difficulty from one place to another. If gravity is weak because it can spread into extra directions, then why are those directions hidden? The honest answer is that they are hidden because they are small or strongly bent, a statement that invites its own questions about how they became so. And indeed, many models connect the shape and size of the extra space to fields whose values settle during fields whose dynamics could in principle leave traces in ancient light or in the distribution of matter today. This is where cosmology and particle physics meet and argue in friendly fashion. Because the same data that tell us how fast the universe grew and how clumps formed can sometimes corner a model that seems free in the lab. It is worth saying clearly what none of these ideas do. Extra dimensions do not let you send a signal faster than light in a way that beats causality. They do not give easy shortcuts across the galaxy that ignore the energy cost of bending geometry. And they do not release hidden energy into your hands without the bill for creating the shape that makes the release possible. The laws stay sober. What changes is the stage on which they act, and with it, the interpretation of why certain numbers are so small or so large. At the end of a quiet walk through these possibilities, you are left with a picture that is at once adventurous and disciplined. Maybe the weakness of gravity is not a flaw in our understanding of the familiar three directions, but a clue that space itself keeps more structure than our senses reveal. Maybe the thinness of the force we feel is the echo of depth elsewhere, and the way to know is not to dream harder, but to measure better, with balances you could mistake for jewelry, with detectors that listen to the tremble of space-time, with telescopes that weigh clusters by the bending of background galaxies, and with colliders that look for the fingerprints of particles that cannot stay on our sheet. None of this promises a guaranteed revelation, but it does promise a way to keep asking an honest question and to accept the answer whether it widens the room or shows that the doors we imagined are painted on. And there is a soft comfort in that, because either way you learn more about how reality hides its simplicity inside structures that take patience to find, a lesson that reaches beyond physics into the way we search for hidden depths in anything we care about. Equations that work without time and still predict reality. Imagine opening a physics book and finding that the master equation on the first page contains no clock at all, no ticking variable to count before and after, only a rule that tells you which arrangements of the world are allowed. And yet, from that silent rule you can still predict orbits, spectra, and the rhythms of a beating heart. So begin with a simple picture that will steady you. Think of a hiking map with contour lines and a marked start and finish. You do not need to know the time at which each step is taken to know the route that best fits the terrain. The route is the path of least effort given the hills and valleys. In the same spirit, there are formulations of mechanics, where the story is told not as a sequence of instant, but as a whole path chosen by an extremal principle. The action of a system plays the role of the terrain, and the allowed histories are those that make that action stationary. For a fixed energy, this reduces to a rule that the actual motion is the shortest path in a certain geometry of the possible configurations. A geodesic in a landscape of shapes, and you can reconstruct the ticks of a clock after the fact by measuring distance along that path, with a ruler built from the energy and the mass in play. In this view, time does not drive the motion. Motion defines time as a measure that keeps pace with the change of the system itself. General relativity deepens the move, because it tells you that time is not a universal stage, but part of the same fabric as space. And when you reformulate that theory for a quantum world, the most famous candidate equation, the Wheeler-DeWitt equation, is striking for what it lacks. There is no explicit time variable, the wave function, of the entire cosmos is a static object that obeys a constraint rather than an evolution law. And yet, we plainly see change. So how can predictions be made? The key is to give up the idea of a single external clock and to read change relationally. Choose part of the system as a clock and ask how the rest behaves when that clock shows a certain reading. This conditional view is not a trick. It is a way to extract dynamics from correlations. It says that what you can actually observe are joint statements such as when this hand points here, that pendulum angle will be there, and those statements remain sharp even when no external time parameter is present. In quantum terms, you treat the clock and the system together and derive the state of one conditioned on the other. And this is enough to predict outcomes that you can check in the lab, which is why careful experiments have begun to demonstrate tiny versions of relational dynamics, with simple quantum devices that play the role of a clock and a system, and show that conditionals can replace absolute times in practice. The same idea carries into other corners of physics, where time seems to slip out of the equations without hurting their power. Stationary states in atoms are found by solving a time-independent rule, yet the predicted colors of light appear exactly where the rule says they should. Because transitions between those states carry definite energy differences that you can see as lines in a spectrum, scattering probabilities that tell you how particles deflect one another are computed from boundary data in the far past and the far future without tracking every intermediate tick. What matters is the full relation between incoming and outgoing states. And in thermodynamics, the summary of a large system is encoded in a state that knows only about constraints like energy and particle number, while the microscopic ticks of the thousands of constituents have been averaged away, if you want a human scale. Example: think of a piece of music written as a score. The score is not an audio tape in time. It is a timeless object that encodes correlations between notes and instruments that will become sound when a musician chooses a tempo. Change the tempo, and the performance changes while the score remains the same. The physics analog is that the underlying equations can be silent about time and still carry everything needed for a family of consistent evolutions. One of the most intriguing proposals that leans into this view is sometimes called the thermal time idea. It starts with a state that describes a system and shows that this state naturally defines a flow, a way of ordering change that for familiar systems coincides with what we would ordinarily call time. In this approach, temperature and the structure of the state together pick out a direction and a scale for evolution, rather than evolution being imposed from outside. Whether or not this exact idea is ultimately right in full generality, it captures a broader moral that keeps showing up across theories. The arrow and the pace of time are not fixed decorations. They are emergent summaries of deeper correlations and of special boundary conditions that the universe seems to have chosen, notably those that put the early cosmos in a low entropy state, so that as correlations spread, we experience a direction from records to futures rather than the other way around. The stopwatch on your wrist is a small machine that maintains a particular correlation between its gears and what you call seconds. It does not define time for the world. It samples a pattern that is already present in the relations among things. For many readers, this threatens to make reality feel like a frozen block, with change as a trick of the eye. But the block image misses the subtlety. A timeless equation does not erase becoming. It says that becoming is a feature of the relations among parts, rather than of an external river. If you carry a camera through a landscape, it records a trail of images in its memory. Each image contains records of earlier events, and none contain records of later ones. The collection of images as a whole is timeless, and yet within the collection there is a clear sense of before and after encoded in the records. The physics version is that the global state may be static, while the subsystems engage in correlated exchanges that let internal observers build a sense of flow and predict what they will see when their internal clocks point at new values. The certainty lies in the correlations, not in a background metronome. This relational way of making predictions also clarifies old puzzles about what counts as an observable. In a theory, without external time, the meaningful questions are never what is the position of a planet at this time. They are always, what is the position of a planet when the hands on a chosen clock show that angle, the second form, can be asked and answered inside the theory, and it leads to the same measurable ephemerides that astronomers publish. Once you train your questions to be relational, the missing clock stops being a problem and becomes an economy of description. You carry fewer assumptions and get the same predictions. There is discipline here, and not free invention. Relational dynamics must match all the precise tests that ordinary time-based dynamics already pass. And when you compute carefully, they do. What differs is the conceptual load. You are no longer claiming that there exists a universal ticker hidden behind the scenes. You are claiming that the world is a web of relations that can be sliced in many consistent ways, and that everything you ever measure belongs to some such slice. It explains why physics can be predictive, even when written in a form that looks at the whole story at once, because the strategy of conditioning on a clock picks out the very sequences that your instruments will read. The last worry to meet is practical. Are there situations where the absence of a fundamental time would change how we build devices or how we plan experiments? Perhaps the answer will turn out to be yes in the places where gravity and quantum rules must be used together, places where clocks made of matter and light cannot be separated cleanly from the geometry they live in. In such places, the old division between a system and an external time may cause contradictions that a relational approach avoids. And even if the effects are subtle, the theory that handles them cleanly will likely be the one that tells us how to read the earliest moments of the cosmos, or the deepest neighborhoods of a compact object with less confusion. But even if everyday practice barely changes, the mental shift is valuable, because it shows why physics can be calm and predictive without an absolute clock, and why you can trust an equation that carries no time label to speak about a world that unfolds. End gently with this thought. A story can be written in two ways, as a diary with dates in the margins, or as a novel that sets relations between scenes so tight that the order falls out when you start to read. The universe seems to have chosen the second option at its deepest level. The diary emerges when small parts of the novel agree to play the role of clocks for the rest, and your life is a thread woven through that fabric. One more set of correlations laid down as you move from memory to expectation. Not because a hidden bell tells you to step, but because stepping is what it means for your inner clock to find its next mark in a world where the script works even before any bell is installed. Temperatures below absolute zero, hotter than infinity. You have been taught that cold bottoms out at a single sacred point, and that nothing can be colder than absolute zero. And then physics invites you to a quieter room, and explains that there is a way for a system to slip past that point, and yet become hotter than anything you can imagine, which sounds like wordplay until you learn how temperature is defined, not by how icy something feels, but by how the number of accessible arrangements changes as you add energy. So begin with a picture that is safer than an ice bath, a set of identical rungs that an atom or a spin can occupy, where the ladder has a lowest rung and also a highest rung. In ordinary conditions, most of the occupants are found near the bottom, and if you feed the system a little energy, more of them climb, and the disorder grows, and the temperature is positive. But if you manage something more mischievous and push so many occupants near the top that the higher rungs are more crowded than the lower ones, then adding yet more energy actually reduces the number of ways to arrange the crowd. The disorder goes down as energy goes up, and by the thermodynamic dictionary, that flip means the temperature has crossed through the infinite wall. And, emerged on the negative side, do not picture frost and blue light, picture a crowded balcony, where the upper seats are more full than the lower seats, and any extra ticket you sell forces you into a more ordered pattern. This is the sense in which negative temperature is not colder, it is beyond hotter than any positive temperature. In the only way that matters for heat flow, if you let such a system touch an ordinary one, energy will stream out of the negative temperature object into the positive one every time, because the first is more eager to shed energy than any positive temperature system is to give it up. The trick is that you cannot play this game with every kind of matter. You need a set of states, with a ceiling as well as a floor, so that there is a meaningful top to crowd. Into a gas of free-flying atoms with unbounded kinetic energy will not do, because there is always room to run faster. But a collection of nuclear spins in a crystal has a highest energy configuration, and so does a cloud of sin, an optical lattice where the allowed motion is chopped into bands like seats in a theater. And this is where the first demonstrations happened, decades ago, with nuclear spins that were coaxed into an inverted population by carefully timed radio pulses, and where modern versions have appeared with ultra-cold atoms. Loaded into a light-made lattice, in those cold experiments the researchers tuned interactions and confining forces so that the atoms effectively had an upper bound to their energy. Then they jolted the system so that many atoms occupied the upper band states, and they observed signatures that matched a negative absolute temperature. The atoms had not been cooled past zero. In the everyday sense, their internal book of states had been rearranged so that the sign of temperature flipped. This odd state is fragile and honest at once. Honest because it does not break the second law. The rule about entropy increasing in isolated systems remains safe. The inevitable direction of heat flow is simply clarified. Heat leaves the negative temperature system and enters anything with a positive temperature. The overall entropy of the combined world still grows fragile, because any contact with uncontrolled uncontrolled degrees of freedom will let the system relax back toward a positive temperature. The population inversion unwinds unless you maintain the conditions that cap the energy and isolate the system from what it might exchange with its environment. Think of it as balancing a pencil on its point. While still obeying gravity, you can do it for a while, with care, but not forever, without constant attention. The most famous cousin of this physics lives in the working heart of a laser, where you create an inversion between two energy levels so that light passing through does not get absorbed, but is amplified. The laser medium can be described as having an effective negative temperature for that pair of levels. And the moment you look at it that way, several puzzles about lasers dissolve. The glowing stick is not colder than the room. It is a device that has more atoms in an excited state than in the lower one, and it gives up that excess eagerly. As a coherent beam, the energy flows out, because the medium sits on the negative side of the wall on the specific ladder being used. There are more subtle consequences as well if you try to draw a heat engine between a negative temperature reservoir and a positive temperature one. The ideal efficiency bound looks larger than one in simple formulas, which alarms beginners until they realize that the negative reservoir is not a free resource. It must be created and maintained with work, and the accounting is only complete when you include the machinery that keep the inversion alive. The engine is not mining a new continent of energy. It is spending energy elsewhere to create the unusual order that then relaxes by doing useful work along a chosen path. Every watt that leaves the negative reservoir can be traced to the effort that set the system up. You might ask if anyone has cooled a whole block of matter to a negative temperature, and the answer is no, and that is the point. A negative temperature is not a universal label for everything. In a room, it is a property of specific degrees of freedom, with a capped spectrum, the spins in a salt, the paired levels of a laser, medium the band-limited motion of atoms in a lattice, and within those carefully corralled arenas negative temperature is both possible and measurable, while the rest of the object stays at an ordinary positive temperature, linked to the unbounded motions of its atoms. There are boundaries to respect, and they make the concept sturdier, not weaker. You cannot cross from a small positive number to a small negative number by gradual cooling. You must pass through the cliff of infinite temperature where all rungs are equally filled, and then jump into the inverted pattern on the other side. You cannot keep the state long without isolation, because any leak into an unbounded reservoir air of motion will bleed away the inversion. You cannot use it to violate causality or to send signals in forbidden ways. It obeys the same local rules as any other thermodynamic system. The only difference is the mapping from energy to disorder. If you let this settle, a gentler meaning emerges. Negative temperature is not an invitation to fantasy. It is a sharpened lesson in what temperature really measures. It reminds you that hot and cold are not emotional adjectives, they are slopes. In a ledger that tracks how options change with energy, it invites you to look at a system and ask whether its allowed energies have both a floor and a ceiling, whether you can herd its occupants in a way that flips the slope, and whether you can keep that herd from wandering. And it gives you tools you can use today in imaging, in secure communication, in precision sensing, anywhere. An inversion can be made to work for you. The deeper romance is that even a concept as homely as temperature contains layers of structure that only reveal themselves when you prepare nature with care and listen long enough at very low noise. The world whispers that below zero sometimes means beyond hot, and that understanding why teaches you more about order, disorder, and the quiet rules that run the show than any thermometer ever could on its own. Electroweak unification. Two forces, one origin. There's a hidden simplicity buried within the chaos of nature, an elegant truth that reveals itself only when we look beyond what's obvious. And one of the most profound of these revelations is that what we once thought were two distinct forces, electricity and the weak nuclear force, are actually two expressions of a single underlying phenomenon, a unity known as electroweak unification. To the naked eye, and even to early science, the electromagnetic force and the weak force seemed entirely unrelated. One governs the attraction between charged particles, gives rise to light and magnetism, powers motors and fuels stars through photons. The other, the weak force, governs radioactive decay, transforms particles into others, and enables the sun's fusion through the change of quarks. One is long-ranged and familiar, the other is short-ranged and subtle. But under the surface of reality, when temperatures soar to the unimaginable scales that existed in the earliest instance after the Big Bang, trillions of degrees in mere billionths of a second, these two forces become indistinguishable. They merge into a single entity described by the electroweak theory, a groundbreaking unification first proposed in the 1960s by Sheldon Glashow, Abdus Salam, and Steven Weinberg, whose combined insight earned the Nobel Prize and reshaped our understanding of the universe's fundamental architecture. In this high-energy domain, the distinctions between electromagnetic and weak interactions dissolve, and what remains is one cohesive force, mediated not by separate rules, but by a unified mathematical framework. This isn't just theoretical poetry, it's experimentally confirmed. The discovery of the W and Z bosons in 1983 at CERN provided the clearest physical validation of electroweak theory. These particles, heavy cousins of the photon, are the messengers of the weak force and gain their mass through interactions with the Higgs field, a mechanism that also explains why the unified electroweak force splits into two distinct behaviors as the universe cools. It's as if, when the cosmic temperature drops below a critical threshold, the symmetry of the universe fractures, and a single elegant force becomes two different ones, each carrying its own role, its own messenger, its own domain. This process, known as spontaneous symmetry breaking, is the quiet fracture that created difference where there was once unity. And at the center of this breaking is the Higgs mechanism, a field permeating all space, which interacts with particles to give them mass and which treats the photon and the WZ bosons differently. That's why the photon remains massless and mediates a long-range force, while the W and Z become massive and act only over extremely short distances. But originally, they were all part of the same electroweak family, twins born of the same principle, diverging only after the universe cooled enough to impose constraints on how that symmetry could manifest. In many ways, electroweak unification is a window into how nature simplifies at high energy. The closer we get to the origin of time, the more distinctions blur. What looks complicated at low energies becomes unified at higher scales. This insight lies at the heart of particle physics' greatest ambition, the search for a grand unified theory, GATI, a deeper framework in which the electroweak force and the strong nuclear force would themselves merge, and perhaps, if we go even deeper, connect with gravity in a theory of everything. Electroweak theory is our first solid step down that road. It's a blueprint for how forces that appear separate can emerge from a common source, how symmetry and its breaking define what's possible, and how the universe's earliest moments still echo through the behavior of particles today. And the more you examine this unification, the more it teaches you to doubt the divisions we assume are natural. Are forces really different? Or are they just different manifestations of a deeper whole? What we call electromagnetism and the weak force are simply two low-temperature behaviors of a higher truth, and it forces us to reconsider the nature of duality, not as opposition, but as divergence from unity, as consequence of cooling. This is not just a lesson in physics, it's a lens for thinking about everything from biology to consciousness. At high energies, complexity simplifies. Differences collapse into symmetry. Distinction becomes expression. And from that point of view, everything we see, light, charge, decay, mass, is a kind of unfolding, not of chaos, but of broken symmetry. It's tempting to think of unification as something abstract, something that matters only to theorists. But Electroweak unification has real consequences. It explains why radioactive decay happens the way it does. It predicts the precise mass and behavior of W and Z bosons, which have been measured with incredible precision. It gives us a framework to understand neutrinos, those ghost-like particles that barely interact with matter but are abundant across the cosmos. And it shapes the behavior of the early universe, where electroweak processes set the stage for the first elements to form, for matter to separate from antimatter, for the seeds of galaxies to arise. And this unity also tells us something about the structure of matter, that even the forces that seem to tear particles apart are connected to the forces that create coherence. Electromagnetism gives us light, chemistry, magnetism. The weak force gives us decay, transformation, radiation. But both spring from a deeper symmetry, a unified equation that under high energy makes no such distinction. This is not unlike how hot iron becomes paramagnetic, losing its directionality, only to form magnetic domains as it cools. The order emerges from a phase change. Symmetry gives way to structure, and structure gives rise to what we call complexity. But underneath, the equation hasn't changed, only the conditions have. And so, when we ask whether nature is inherently diverse or inherently unified, the answer is both. But unity comes first. Diversity is what happens when unity cools. And perhaps, hidden in that cooling, is the story of why our universe feels both structured and dynamic, both stable and capable of change. Electroweak unification is more than a technical achievement. It's a philosophical invitation to reconsider how we draw lines. The universe did not start with 4 forces. It started with fewer, and those fractured as the universe aged. What we experience now are differentiated behaviors, sculpted by cooling, shaped by broken symmetry, and carried forward by fields that still whisper the unity they once held. So the next time you flip a light switch or hear the word radiation, remember that these aren't separate domains. They are distant cousins from the same ancestral force, divided only by the cooling of time. And the next time you wonder whether difference means disconnection, look closer. The electroweak force says otherwise. It says that deep under the surface of contrast lies coherence. It says that what's broken was once whole, and maybe again under the right conditions. And perhaps that's the most beautiful message physics can offer. That even separation can contain the memory of unity. That even forces pulling in different directions can be bound by a common past. And that sometimes, understanding what holds the world together means looking beyond the names we've given things and asking instead, where did they begin?